actual arterial stick. If you drop down the bottom of page 6, letter C, it says the results will show a consistent correlation with pH and PCO2. However, letter D says PO2 does not correlate well with the actual arterial blood if you're using a capillary sample. This is especially true when the arterial PO2 is above 60. So capillary samples have limitations. That's the take-home message here. You can use them for getting information about pH and PCO2, but you cannot really trust the information they give you about PO2. So if you're trying to determine whether or not you've got adequate oxygenation for the patient, you need to get an arterial sample as opposed to a capillary sample. All right. Top of page 7, number 3, umbilical artery lines. They're used for newborns. We give you information about that and show you an illustration of how that's set up. Do the same thing for number 4 there on page 7, arterial line. I give you the example of how it's set up with the flush system and all of that. The main thing I want you to point out there is at the bottom of page 7. That's letter D, the sampling technique. Highlight number 1. Remember that you need to withdraw approximately 3 to 5 mils of fluid from the catheter. And what you're doing by withdrawing that solution is you're clearing out all of the heparin that's from this point, okay, all the way back up here to where you're sampling. All right, so that whenever you attach the syringe on here, now when you draw out, all you're pulling out is blood. You don't have any contaminated heparin in the sample. Top of page 8, blood gas analyzers. Remember that the blood gas analyzers, number 1, directly measure the following. We've already mentioned this once. They directly measure PCO2, PO2, and pH. That's an important. Everything else, okay, number 2, all the other values like saturation, bicarb, all of those things are calculated, okay? Unless you've got a blood gas analyzer that has like a hemoximeter in it, all right? But at the MBRC, there's don't. So that's what they're kind of going by. They got the simple analyzers. Drop down to number 4 there, quality control or QC. This is some new information that's on the test. Letter A, basically, you're going to use commercially prepared controls to evaluate your blood gas as far as its accuracy. Highlight number 1 under letter A there. There's 2 types of emulsions, the aqueous and the fluorocarbon-based. Drop down to letter E at the bottom of the page 8. Typical malfunctions would include the following. We've got those listed there. But the main thing you need to remember about any malfunction is letter G. When the blood gas machine is functioning correctly, the measured control values will be close to the mean within plus or minus 2 standard deviations. So we're going to talk about that here in just a minute as far as how you go through and evaluate your blood gas analyzer to see if it's working or not. Top of page 9, number 5, the Westgard rules. Highlight, this is also new information on the test. Highlight letter B, this is the method of quality control, and it's called the multiple rule method. And letter C, some examples of this under number 1 there. Warning situation, this is when one control or observation exceeds the mean by plus or minus 2 standard deviations. And we'll talk about, they'll show you this on the Levy-Jennings plots. It'll make a little bit more sense if you look at those. Number 2, the out of control situations. I'll highlight letter A there. That's basically if you have one control observation exceeds plus or minus 3 standard deviations. Letter B, if you have 2 consecutive control observations that exceed plus or minus 2 standard deviations. And then letter C, the differences between consecutive control runs exceeds 4 standard deviations. Again, we will show you here in the Levy-Jennings chart in just a minute what those examples of those are and how you would identify that for the test. Highlight letter D at the top of page 9. When using the multiple rule method, a history of the control runs have to be kept, so you got to keep records. Letter E, this is accomplished by using a control chart, usually called the Levy-Jennings plot. Okay. Letter G, each individual control result is going to be plotted and then tracked for that particular electrode. And then letter H, applying the multiple rule method for interpretation allows out of control situation to be detected sooner. So in number 6 there, we have a Levy-Jennings chart here, several, and it doesn't matter. I mean, you'd have each one of these graphs for each electrode. So one for the pH, one for the PCO2, and one for the PO2. All right. So this first one here is an example of showing you that the electrode is actually in control, because what you're doing is you're running the controls. This could be like at 8 o'clock, this could be at 12 o'clock, this could be at 4 o'clock, this could be, 8 o'clock at night or whatever. But every time you run a control, it's plotted on this graph. And so you can see here is +2 standard deviations here, and here is -2 standard deviations. So any of these plots for any of these graphs should be between those two lines, the +2 standard deviation and the -2 standard deviation. As long as the plots for the controls are between those two lines, that's considered to be an in control situation, and you can trust that blood gas analyzer to give you accurate information. All right. But how do you know if it's not in control and it's in a situation that may give you inaccurate information? Well, here's the first example. Here's an example of everything is within ±2 until we get to this point right here, and then it jumps up to +3. It's out of the ±2 standard deviation range. And so this would be, but everything else beyond that is back in range. So this would be a warning if you saw something like this. If everything was going along good when you ran your controls and you just had one event that was outside of the +2 or -2 standard deviation, then you would say, okay, I need to watch this electrode to make sure this thing's continuing to work properly. All right, so that's why they call it a warning. Here is a situation where at the bottom of page 9 there is you've got everything that's going along fine within the ±2, but then you have this one that's way out here. It's above +3. Okay, and because it's above +3, that's considered to be an out of control situation. All right, which means that you cannot trust this analyzer. So you cannot trust it. It's not working properly. You've got to fix it. All right, and we'll talk about how to fix that here in just a minute. The next two that we've got are also out of control situations. So here again, it's the plots are within ±2 standard deviations, but then you have two plots that are outside of the ±2 standard deviation. In this case, it's a minus greater than a -2, not quite a -3, but because they're two, one right after the other, then that's an out of control situation, and now you've got a broke blood gas machine, right? You've got to fix it. The last one here, we've got a situation where you have everything in control, but then you come down here, it's at a -3 standard deviation, and then up here is a +2 standard deviation. So the difference between these two is actually 4 standard deviation, greater than 4 standard deviations. And so because you have the difference between those of greater than 4, that means that this analyzer or this electrode is not working either, and you cannot trust that analyzer. All right. So on page D10, the top of the page there under the graph, letter C, it says what you're supposed to do if you've got an out of control situation. Out of control situations require the electrode to be recalibrated or replaced. That's going to be your action on this test. You're not going to have to do a bunch of troubleshooting on blood gas analyzers on this test, because they've already got 2 tests where they test therapists who basically take care of blood gas analyzers. And so they just want to know if you know the basic concept of how do you know if it's broken and whether or not you can trust the information it's producing for you. And so that's the piece that you need to know. All right. Highlight number 7 there. Other quality control methods. You can kind of read down through those. Number 8, point of care testing. Under that, highlight letter A. This is any lab testing that's done at the bedside. And basically, the point of care testing, you might want to just jot these two words down next to it. Quicker results. I mean, that's the only reason you do point of care testing, is to get the results quicker. All right. They give you the same information, it just gives you quicker results. Top of page 11, letter C, calculation. So this is the part where you got to take a deep breath if math is not your favorite thing, and you got to just trust me. And I'll say that laugh, I shouldn't laugh. You got to trust me that I'm going to help give you some information that'll make this process of doing calculations easier. Now, you remember John, he's got a calculation that he refuses to do. That's the what? That's right, the Fick equation. And so there may be one of these calculations that you don't want to do, and that's okay, because if it gets you confused and gets you all frustrated, I don't want you to do it either. All right. But the majority of these calculations that they're going to have on the test are not too bad, especially whenever you use our shortcuts. And as a result of that, that means that I'm going to get more points. Okay. So a couple things I want you to think about. There's some very specific MBRC rules that I want you to write in your study guide next to number one or under number, or next to number one on the left-hand margin. Excuse me just a minute. So here's the first MBRC rule. First of all, rule is that calculators are going to be available on the test. Again, it's going to be a calculator inside the software. You can't bring one to the test, right? So you will have a calculator. So that's better. That's good news for a lot of people, because up until, you know, this past year or so, everybody could, I mean, no one could use a calculator on the test. All right. The second rule that I want you to write down is that there can't be more than one answer. There can't be more than one answer. And because there can't be more than one answer, that means we can estimate, because they got to keep the answers far enough apart away from the correct answer so that you get it right. All right. The third rule is that the MBRC is going to keep the numbers simple. So if they keep them simple, that means you know, if you know your normal values, that's going to give you an edge, like normal values for some of these calculations. You'll be able to kind of look at information and say, well, if these things are normal, then that means the calculation's got to be normal. And that just means the whole thing, the interpretation of the calculation, is going to be normal. All right. So there's going to be some calculations, and not all of these calculations will be on the test. All right. But there will be a couple that you will definitely see, and we'll identify those for you. But again, if you know how to do these, then, and they're easy enough for you, then I definitely would take the time to review them and to make sure that you're able to use them, because like I said, it'll just give you the opportunity to get more questions correct. All right, and that's what you want. So it kind of adds to your thing here. All right. So I already gave you the pep talk. So again, if you need to go to your happy space for a minute before we get started, that's fine. We're going to start off a real easy one here, though, and that's the alveolar air equation. Everybody knows this one, because this is the first one you learn probably in your program. And again, you can see there, highlight number one there, and then the example letter D gives you the formula and so forth. So whenever you do this one, we give an example there, letter D. Here, if you're calculating, if you've got a patient's on 50% and a CO2 of 40 and a barometric pressure of 747, you put all of that stuff into the formula. The barometric pressure goes here, okay? Water vapor pressure is always 47, or assumed at 47. FiO2 is going to go here. The PCO2 is going to go here, and then you're going to divide by the respiratory quotient. And then you just go through and do the math. Now, you can do this and come out with the answer of 300, and, you know, that's fine if you want to do it that way. This may take a little bit more time. we have a shortcut for this. Now, the shortcut is not in your book, so you may want to take a picture of this or a screenshot of this whenever I show it to you. Here's the shortcut. All right, and I'll give you a chance to take a screenshot or a picture of it. And so this is PaO2 is equal to 7 times the FiO2 minus PaCO2 plus 10. All right, don't ask me where the 10 comes from or where the 7 comes from. This is just the shortcut. All right. Now, Tom may be able to tell you, but I can't. All right. The neat thing about this shortcut is that it allows you to use a whole number for the FiO2. So again, if you're not using a calculator, it makes the math a lot easier. And so if we take that same situation that we just had of 50% oxygen and a CO2 of 40 on that last example we just gave you in the book, notice how this thing comes out. The 70 times 50 is 350, and then the 40 plus the 10 is 50, so it's 350 minus 50, that's 300. You could actually do that in your head almost, okay? So that's a great one. That's a great shortcut. I like that shortcut, and like I said, it'll save you a few minutes on the test if you have to do that one, okay? Number 2 is an easy one as well. This is the AA gradient, and again, if you just calculated the P big AO2, all you got to do is subtract the arterial PO2 from it, and that's going to give you your gradient, okay? And so here's an example, same example from the previous, same AA gradient, and the arterial PO2 is 80. So you plug this formula in, the PbAO2 of 300, the PaO2 of 80, then you subtract the two, you come up to 220. So that's a very easy one to do. The most important thing, though, about AA gradient is how to interpret it. And so you can see the interpretations in the box down there at the bottom of page 11. So highlight letter F there. That's a good one to remember. If you've got an AA gradient that's greater than 300, you've got a shunting situation. If it's between 66 and 300, you got a BQ mismatching, which means that you're going to give them oxygen. And if it's between 25 and 65 on 100%, that's considered normal. And again, if you got a shunting problem, then what you're going to do there is you're going to give them PEEP. All right. Top of page 12. So I could do both of those. All right. Those two aren't very hard. All right. The next one here is the PF ratio. And the PF ratio is also a very easy one to do because all you're doing is taking the P big AO2, all right, and dividing the FiO2. And remember, the FiO2 is in decimal form. Now, that used to be a little bit difficult on the test because you didn't have a calculator, and so sometimes you may have forgotten how to do that. But it's a very simple formula to do because, again, it's just PF ratio. The most important thing about the PF ratio is this box, and this box is listed there in letters E, F, and G. So you've got this box, but it's not in a box format. But I would highlight letters E, F, and G because you need to know how to interpret the PF ratio. So if you have a PF ratio that's greater than or equal to 380, that's considered normal. If a PF ratio is less than 300, that's considered acute lung injury. And if you have a PF ratio less than 200, that's considered ARDS. All right, so that's the most important thing about the PF ratio is not how to interpret it. Okay. So I could do that one. I mean, that's not a hard one to do either. The next one there, number 4, is the arterial oxygen content. This is one I'm sure most of you know. Remember, the first part of the equation relates to the oxygen that's bound to the red blood cell. And then the second part of the formula is related to oxygen plasma. So highlight letter C there for the formula and highlight letter D for the example. So if we do an example, we calculating the CaO2 for a patient has an SaO2 of 98%, PO2 of 90, and a hemoglobin of 14. We take that information and plug it into our formula. The hemoglobin goes here, the 14. That's our constant, the 1.34. The saturation would go here. Okay, the PaO2 goes here, and whenever you do the math, you come up with this piece right here. Okay, the 18.76 is what 14 times 1.34 is. Then the saturation is 0.98. And then adding 0.27, which is what 90 times 0.003 is. All right. So you run the math there and you come up with the answer of 18.7. All right. I've got two shortcuts for this one. All right. Actually, there's more, but I only give two because if I give you too many more, you won't know which one to pick. You'll spend more time trying to figure out which one you're supposed to use. So I'm only going to give you two. All right. So here's the first shortcut. So get your camera or your screenshot button ready. So here's the first shortcut. What you're going to do is you're going to skip the amount of plasma. So in other words, this piece that was over here that you added to PO2 times 0.003, you're just not going to do that because that's such a very small number. It doesn't change the overall answer that much, right? So what you'll do is take the hemoglobin, multiply it times 1.34 and then times the saturation. Whenever you do that, okay, you come up with 18.4, which is very close to 18.7 in the last calculation. And that's close enough for you to get the answer correct. Again, you may not see 18.4 in your answer on the test, but 18.4 is very close to 18.7. And so that's the answer that I'm going to pick. I'm going to pick the answer on the test that's closest to the answer I come up with on my shortcut. All right. So that's one way. Here's the second way. Shortcut number two. Don't do the math. And some of you are like, what? What's he talking about? Well, if you've got this condition, if you've got all the values are normal for the CaO2, or all the values are normal, then the CaO2 has to be what? Normal. All right. So in other words, if you have a normal hemoglobin, if you have a normal SaO2 and a normal PaO2, what is the answer to your calculation have to be? It's got to be within normal limits. And this is the normal limits for the CaO2. You can see that on letter E there. Highlight that. And I would draw a circle around my favorite number right here. Okay, that's the number I remember about O2 content is 20 volumes percent, right around 20 volumes percent. You can see 17 is a little bit less than 20. All right, but CaO2 should be right around 20 volumes percent. And so that's what I use that as my memory tool. All right, John's favorite number. Now, if you go down to number 5, the mixed venous oxygen content, and you can see here that that formula is very similar. I mean, I could do the O2 content one. That's not a problem. And so if I can do the O2 content one, because this one is very similar, I could do this one also. Because you can see here, you still got to have a hemoglobin. You're using SVO2, not the SaO2. All right, because this is a venous sample. And you're using the PVO2, not the PaO2, all right? So this is a venous sample. We're trying to find out how much venous oxygen content we have, all right? And so if you take that, you run the shortcuts are basically the same. You could skip the plasma, the amount in the plasma, which is the CVO2, is equal to the hemoglobin times 1.34 times the SVO2, all right? But you could also do the second shortcut, which is don't do the math. But you got to know what the normal values are for PVO2, SVO2, and CVO2, all right? You may want to take a picture of this slide because this has got all those normals right in there for you. So if I have all these normal values, then that means that my CVO2 is going to be normal. All right. Now, the highlight I gave you, letter F is the normal value for that is between 12 to 16, but I always write off to the side of there the CVO2 of 15 volumes percent. So you might want to just write 15 volumes percent next to letter F, and I'll show you why that is here in just a minute. So below F there, I want you to highlight letter G and letter H because this statement up here on the slide is what is saying the same thing that those two letters are saying in your study guide, okay? So you've got this in your study guide. You don't have this part in your study guide. So if you want to take a picture of this one, you can. That's fine. So the thing to remember here is that if the CVO2 gives us an indication or reflection of what's going on with our cardiac output. And these two have a direct relationship with one another. If the CVO2 goes down, then that means the cardiac output goes down. And the same thing here with the SVO2. It has a direct relationship to cardiac output also. If the SVO2 goes down, then the cardiac output goes down. But here again, you cannot interpret this unless you know what these normal values are, because you got to know what a decreased SVO2 is before you can interpret. So you really need to know these venous values just like you know your arterial values. If you don't, you're really going to miss a number of questions on this test. So, because here again, cardiac output, is that a life function that we've talked about? Absolutely, that's circulation. And so are they going to ask you a lot of questions about a life function on this test? You better believe it. And you got to know how to evaluate it in a number of different ways, not just one. And these venous values are an excellent way to help us remember to think about cardiac output. All right. So anytime you see venous values on this test, I want you to be thinking about cardiac output. And I also want you to be thinking about what the normal values for those are, because you got to know what the normal values are to interpret them. All right. Just like blood pressures for your hemodynamics. If you don't learn those blood pressures, that circle diagram's not going to help you. Okay. So you got to learn the blood pressures. On this, you've got to learn the mixed venous values. All right. Let's see. So number 6 is the arterial venous content difference, which basically what we're doing is taking the CaO2 and subtracting the CaVO2 from it. Now you could do that very easily by just calculating both of them. But there's a shortcut for calculating this also. And the shortcut is this. So you may want to take a picture of this or a screenshot. Just take your SaO2 minus the SVO2 and multiply it times 0.2. Now I know there's people out there asking, well, what's the 0.2? That's just a constant, right? Don't ask me where it came from, or Scott, the guy who owns Kettering, he's probably the one that came up with it, or Tom did. Those are the real smart guys in the organization. And so I'm sure they probably put their heads together and came up with that, but I have no clue where it came from. So don't ask John that. Just this is what it is. This is the shortcut. And again, if you do the shortcut, it's pretty easy. You'll come up with basically the same thing. As you can see here in this example, again, if you want to take a screenshot of that, that's fine. What is the CaVO2 if the saturation SaO2 is 95% and the SVO2 is 70%? Well, you just calculate 95, or take 95 minus 70 times 0.2, and that gives you 5 volumes %. Now, here's another thing. The one thing that I know is that normal value for the content should be about 5 volumes % different. So again, if we said the normal CaO2 is 20 volumes %, and we said the normal value for CVO2 is 15 volumes %, the difference between 20 and 15 is 5. So that's where that came from, 5 right here, right? So if I've got a normal SaO2 saturation, and I got a normal SVO2 saturation, that means that my venous AV difference has got to be normal also, right? So that's just another way of looking at it. That's the don't do the math part. If the CaO2 and the CVO2 are the normal, again, you got to know what the normal values are, then the CaVO2 must also be normal, right? Within 4 to 5 volumes %. And that's letter D. So if you haven't highlighted letter D, make sure you do that. Also highlight letter F. You need to know what the relationship is of the CaVO2 difference to cardiac output. And this is the relationship in letter F. You've already got it in your book. So if you highlight letter F, you've got this. If you have an increase in CaVO2 difference, then that's going to cause your cardiac output to go down. So the relationship between cardiac output and AV difference, CAV2 difference is indirect, okay? It's indirect. If one goes up, the other one goes down. So that's different than the CaO2, the CVO2 and the SVO2. SVO2 and CVO2 have a direct relationship with cardiac output. Okay, so they go in the same direction, but this one, it goes the opposite. So here again, make sure you check out and remember what this venous, the venous means that it's relating to cardiac output. And again, anytime you see something that has a PVO2 in it, an SVO2 in it, or CVO2, you need to be thinking cardiac output. All right? Because that's why they're giving it. Very seldom will they actually give you a literal cardiac output on this test. But boy, they'll give you a ton of this venous stuff on the test. Okay? So make sure you, because again, in the matrix, it talks about the stuff a lot. That's why I'm telling you that. All right. Top of page 13, cardiac output. And again, we know this is the Fick equation, which is the equation that John doesn't like to do. Again, we've got it listed there for you. You certainly are welcome to learn it and to use it if you want to. All right. But for me, again, what I'm going to remember is cardiac outputs between 4 to 8 liters a minute. And so if I see a normal AV difference and I see a normal oxygen consumption, then I'm going to say, hey, my cardiac output's within normal, all right? And vice versa. If I see that this is normal and this, I'm just going to look at these numbers here to come up with an answer as opposed to trying to do the calculation, all right? But we give you an example of how to do it so you can kind of see how the math works and so forth, so you can kind of work down through that. But the big thing is remembering letter D on the bottom of page 13 there, the normal value, 4 to 8 liters a minute. That's an important number to remember. And we've already talked about that when it comes to hemodynamics. All right, Shunt equation. Now, some of you are probably looking at this one and saying, oh, yeah, that's my Fick equation. And I thought that too. I always had problems with the Shunt equation. That thing was just like, oh, man, I don't want to do that until I went to Kettering. And since I've been to Kettering, I'm like, boy, give me a Shunt equation anytime you want to, MBRC, because I'm going to get that one right. So you can see this is pretty intense math here, okay? A lot of different stuff. The normal value for the shunt should be between 3 to 5 volumes, 3 to 5%. But here is the shortcut, okay? I'm not even going to talk about the math on the other. This is the shortcut. So take a picture of this, a screenshot, whatever you want to do. This is the shortcut and how we recommend you to do the Shunt equations on this test. All right, so the first thing you're going to do there is you're going to look at the A gradient. And then step 2, for every 100 torr in that AA gradient, you're going to add 5% shunt, okay? And then the third thing you're going to do is you're going to add 5% for the normal. So what we've done in this shortcut is, what we've said is, how do we know how much abnormal shunt we got? And that's what step 2 tells us, all right? That's how much abnormal shunt we got. But there's also a normal shunt. Everybody has at least, 3 to 5% normal shunt. We already told you that's what's the normal, all right? So we got to add steps 1 and 2 together in order to get the total shunt. Now let me show you how this works. And again, if you want to take pictures of these images or these slides, feel free to do so. So here's the shortcut. Here you got an ADO2 that's 300, all right? And they want to know what the shunt is. So basically, how many hundreds are there in 300? Well, that's pretty easy. There's 3 of them. Okay, so I'm going to take that 3, and for every 100, I'm going to multiply by 5%. Remember, for every 100, I'm multiplying 5%. So there's 300s in there. So 3 times 5 is 15%. So this is the total amount of abnormal shunt in this situation. Is 15. That's how much wasted perfusion, non-oxygenated blood. All right. Now I've got to add the 5% shunt for a normal shunt to the 15 to get my total shunt, and that's 20%. Okay, so 15 plus 5 is 20%. all right? So again, steps 2, I'm looking at abnormal shunt only. Step 3 is I'm adding my normal shunt to my abnormal shunt to get my total shunt, all right? And trust me, that works great. Like I said, every time I see a shunt equation on the test, I'm like, oh yeah, I'm getting that one right. Okay. That brings us to number 9, middle of page 14. Arterial oxygen saturation. What we're doing here is we're trying to estimate what the PaO2 is with a particular saturation. Okay, and it can be estimated by subtracting 30 from the SaO2. And so basically what you see here is how that will work. But what I would like to do is point your attention down here to the 60/90. Most of us remember from our classes, our blood gas classes, that if we have a PO2 of 60, that's going to give us a saturation of about 90%, right? So what I do is when I'm looking at the pulse ox, if I see, okay, the patient's got a pulse ox of about 90%, then I know that their PO2 is probably going to be somewhere around 60. All right, that's how you would use this. So the difference between 60 and 90 is 30. And because I know what the relationship is between these two things, I can use it for other percentages or other saturations also. So like 80%, 30 minus 80, or excuse me, 80 minus 30 is 50 torr. So for our saturation, if the pulse ox is showing 80%, one, I can't really trust it, but if it's showing 80%, then that means my approximate PO2 is going to be around 50, all right? If my pulse ox is showing 70, that means my PO2 is going to be around 40. So again, it's just a way of estimating what the PaO2 is by looking at the pulse ox, okay? All right, that brings us down to the bottom of page 14, number 10, oxygenation index. This is not a formula that you'll typically have to calculate, but it is a formula that you need to know because basically highlight letters D and E and then highlight letter F, because basically if you have an OI that is greater than 40, that means it's ECMO is recommended for newborn. All right. So if you have an OI that's greater than 40, you're going to recommend ECMO. That's what you're going to do. All right. Top of page 15, the dead space. Most of us remember how to do this from school. There's no shortcuts for this one. The only thing is the acronym PACO minus PICO divided by PACO. All right. So that's kind of my memory tool to kind of help remember that. Remember the normal value is 20 to 40%. So highlight letter B there, and then we give you an example of how you would go through and calculate that. Here we got an arterial CO2 of 40 and end-tidal CO2 of 30, which these are normal. So you would expect the VD to VT ratio to be within normal limits too. And so if you do the math, you see that it comes out to be about 25%, and that would be considered normal. But once again, the arterial CO2 is normal, the end-tidal CO2 is within normal limits, and so the answer down here should come out to be within normal too. So I generally would just look at these numbers here to kind of come up with what may be going on down here and not worry so much about doing the calculation. But that's just me. Okay. All right, next one on page 15, number 12, the desired minute volume. Again, this is just a way of more precisely estimating how much tidal volume and respiratory rate would be needed to achieve a particular PaCO2. And so basically what you're doing is you're looking at the current CO2 on this side, whoops, back up, on this left side, and then what the desired CO2 is over here on the right side. And so we give you an example, letter C there. What if you had a situation where the patient has a minute ventilation of 8 liters a minute, and on that minute ventilation, the CO2 is 50? How would you change the minute ventilation that's required to get a CO2 of 40? And you could use this particular formula, all right? So here's how you would set the formula up. You take the 8 liters times the 50, because these are the two that are known values. We want a new minute ventilation, and we're going to multiply that by the desired PCO2 of 40, okay? So whenever you run the math, okay, and isolate the unknown, then basically what you're going to have is 400 divided by 40, and that's going to equal 10 liters a minute. So that's one way you could do it. For me, what I'm doing is I'm looking at, okay, at 8 liters at 50, that means I'm not ventilating enough. I need to ventilate a little bit more, okay? And so what I would be doing is saying, all right, I need to give more minute ventilation to get it down to 40. And, that's why I would just, 10's pretty close to that. I would just, probably go on with the number 10. Just something that's a little bit higher than 8 is what I would be looking for in the answer. Okay. So those are a couple ways to look at that one. All right. Top of page 16, interpretation and management of blood gases. Now, here's the thing about this. I know you've been taught how to do things in school as far as interpreting blood gases, but at Kettering, the question we want to ask you, do you know how to do it the way the MBRC wants you to do it, the MBRC way? So what we're going to do is we're going to teach you the MBRC's way to interpret blood gases, and it's so much easier than what we taught you in school, all right? So here again, but there's pieces of information that you've got to, know in order to be able to interpret this information correctly, all right? So we start off here on page 16. We've got a box. You got to know what the normal values are. And you can see up at the top of your box there, we've got the CO2, the PaO2, and the pH, all right? And you need to look over to the right-hand side where the column that says acceptable, you need to highlight those acceptable ranges, all right? The other thing that I want to point out to you is notice that this is the order in which we want you to look at the blood gases. We want you to start off by looking at CO2. Why do we want you to look at CO2 first? Because we said, what was the first life function? Right, ventilation. So right ventilation over here to the left-hand side of the PaCO2. So to remind you why you're looking at that first, okay? Now, what did we say the second life function was? That's right, oxygenation, and there's your PaO2. And so next to the PaO2 on the left-hand side of that box, I want you to write oxygenation, all right? So the first two life functions that we evaluate in the blood gas are ventilation and oxygenation. The third thing we evaluate is the pH, okay? And so that's the third thing. Acid-base balance is the third thing we evaluate in the blood gas, all right? So that's the blood gases related to life functions. If you drop down, all the rest of the stuff in the box, the SpO2, BE, hemoglobin, all that stuff is optional, all right? We want to be able to evaluate the patient. Hey, are they ventilating and are they oxygenating? Those are the two life functions. Those are the most important, okay? Now you drop down to the bottom box there, and this is the box that kind of gives you the protocol of how you're going to interpret the blood gas for CO2, and then what you're going to do to fix the problem. All right, so this again, this is a very, 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 very important box. All right. So you see here on the box on the left-hand side, it says that if we have a CO2 on the test between 35 and 45, we're going to consider that to be normal ventilation. And our response to that is we're not going to change any ventilation settings. We're not going to put the patient on a ventilator, all right, if they've got that 35 to 45 CO2. If we have a CO2 that's above 45, okay, if we have CO2 that's above 45, then we're going to interpret that as the patient is not ventilating. And what we need to do is if they're not already on a ventilator, we need to initiate ventilation. If they're already on a ventilator, then we need to remove any dead space. If they don't have any dead space, then we're going to increase ventilation. So that's your action plan if we've got a CO2 above 45 on this test, all right? If we have a CO2 that's below 35, that means that the patient is ventilating too much or hyperventilating. And remember when we said yesterday that if the patient is hyperventilating, we want to check the PaO2 first to see if they have a decreased PaO2. And if they do, then we're going to give them oxygen, right? If they don't have a decreased PaO2, then we said there's probably a metabolic problem. So we need to figure out what kind of metabolic problem it is and fix it. So that's what this kind of ties in directly with what we've already said. If we're on a ventilator and we got a CO2 less than 35, we need to decrease ventilation. And then we need to also evaluate why. Okay. Now, underneath this box, again, if you've not highlighted that entire box, this box is very, 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 very important for you to know. All right. Because it gives you instructions on what to do when you see these CO2 ranges. So you got to know this box like you know your blood gases. All right. Underneath the box there on page 16, there's an exception, letter B. It says an abnormal CO2 with a normal pH, don't change ventilation. It could be a COPD patient, so keep that in mind. All right. Now let's practice a blood gas here and see how we would do this. So here's the patient has the following ABG while breathing room air. And we notice the first thing we look at is the CO2. We ask ourselves, hey, are they ventilating? And the answer to that is no. Okay. And so what will we need to do for this patient? We need to put them on a ventilator. Okay. Even if they don't give us anything else, they're not ventilating. They need assistance with ventilation. Okay. So what is the patient's primary problem? It's poor ventilation. But some of you saw on that blood gas, oh, but they got a bad oxygenation too. So they need oxygen too. And notice in the answer, they give you both options. But what did we say is the first priority? What's the first life function? Ventilation. That's why you're picking A and you're not picking B. Okay? Because if you improve ventilation, what do you think is going to happen to oxygenation? It's going to get better also. So that's why we keep these blood gases interpreted in an order of priority. Okay? So that would be the right answer. The respiratory therapist should do what then? Well, we need to ventilate them. Well, the only answer that says mechanical ventilation is this one right here. All this other stuff is dealing with oxygen. And some of you say, yeah, but we always go to CPAP before we put them on a ventilator. Not on this test. If they're not ventilating, you better ventilate them or you're going to get it wrong. Okay, ventilation is the highest priority on this test. All right, that takes us to the top of page 17, oxygenation. So that's the next thing we need to be able to interpret. In order to interpret oxygenation on this test, you can see under letter C there, it says that you've got to look at the PaO2 and the FiO2 and answer that question. How's their oxygenation? Is it good or is it bad? And then we've also given you another box. Again, I would highlight that entire box because, again, this is going to be your response on how to fix problems with oxygenation on this test. If you don't know this box, you're going to be probably moving in the wrong direction in choosing what's the best answer. All right. So here again, if you have a PaO2 between 80 and 100, and let me back up just a minute here. This box looks like it may be intimidating, but actually this is probably stuff that you've heard before. It just may have not been put together in the same format. Okay. So don't let this box overwhelm you. As we go through it, you're probably going to say, oh, yeah, that makes sense. That makes sense. Okay. And it's not going to be that hard to remember what you need to do. So PaO2 is 100, 80 to 100. On an FiO2 of 21 to 100%, that's going to be interpreted as acceptable oxygenation on the test. And our response on the test is going to maintain any settings, no change in FiO2 or anything. Check the SaO2 and hemoglobin to make sure those are acceptable, okay? Because again, if those aren't good, then you don't have good oxygen carrying capacity, and you need to fix that. If we have a PaO2 that's less than 80, we're going to call that hypoxemia on a room air up to 60%, okay? And that means there's only two things that can cause the hypoxemia if we have the FiO2 is in this range, 21 to 59%. It could be poor ventilation, and that would be determined by looking at see if they got a high CO2. And then the second would be VQ mismatch. And that means basically the CO2 is normal. So that just means this would, the VQ mismatch is the cause. All right. So there's only two things that can cause bad oxygenation on 21 to 59%. That's poor ventilation and VQ mismatching. So if it's not poor ventilation, then it has to be a VQ mismatch. All right. Now, Here's the solution to poor ventilation. Well, we've already said this. You increase ventilation. Guess what the solution is to a VQ mismatch? We've already said this before. You're going to put them on oxygen. And again, you're going to increase the FiO2 up to 60%, right? Once we get above 60%, we got to treat the problem, the hypoxemia, a different way, all right? And that's where this next one comes in. If we have a PO2 that's less than 80, and the FiO2 is on 60%, up to 100%, then that means one of these three problems is being caused: shunting, refractory hypoxemia, or venous admixture. All right? Now, does anybody know what the difference is between shunting and refractory hypoxemia is? Yeah, there's no difference. They mean the same thing. What's the difference between refractory hypoxemia and venous admixture? None. They mean the same thing. So all three of these mean the same thing. But guess what? Everybody that's in earshot of my voice knows what shunting is. But guess what term they will typically not use on this test to describe a shunting problem? The word shunting. Because they know everybody knows it. Guess what they like to use on this test? They like to use the word refractory hypoxemia. They like to use the word venous admixture. So on this test, you got to remember that both of these things mean the same thing, right? And if we have any one of these three problems, anytime we have an FiO2 greater than 60%, that's what the problem is. If we have these problems, that means we're going to put them on PEEP, all right, or CPAP, right? If we have a PO2 that's over 100, on 22 to 100%, that's over oxygenation. We're going to decrease the FiO2 or PEEP and CPAP. And notice underneath the box there, it gives you the order in which you would decrease the FiO2 or CPAP. It says you're going to decrease the FiO2 till you get it at or above 60%. And then once the FiO2 is below 60%, then you're going to drop your PEEP or CPAP. All right, so we get this FiO2 down to 60% or less, and then we start dropping our PEEP. That's the order in which we would do that. Okay. Now, we got an example of interpreting this blood gas here. So here we are. Patients breathing room air, and they got a CO2 of 41, but they got a PO2 of 70. So what does that mean? What's causing my problem with my oxygenation here? I've got good I've got good ventilation, but bad oxygenation. Is my problem with ventilation? Nope. It's got to be with, yeah, look on your box there. VQ mismatch. How do I fix a VQ mismatch? I give them oxygen up to 60%. Okay. So again, what can cause a room air PO2 of that? I'm going to increase. If I have an increased CO2, I'd ventilate them for the VQ mismatch. But again, it's not the increased CO2 because the CO2 is normal. Okay. How about this one? Patient following blood gas, he's got a CO2 of 26 and the PO2 is 68. Again, this is on room air. So again, the question we're going to ask ourselves is, what could cause this PaO2 on room air? Is it because they have an increase in CO2? Nope. It's then because they've got a problem with VQ mismatch, right? Which is in that on your box there. Okay. Here's one with a patient at 60%. So anything over 60% is a shunt or refractory hypoxemia or venous admixture, right? So they're on 60%. So any hypoxemia on this is those three problems with shunting, okay? So do I have a problem with CO2, with ventilation? Nope. Okay, but do I have a problem with oxygenation? Yes. And what's causing the problem? Well, because I'm on 60%, it could be shunt, refractory hypoxemia, or venous admixture. All those mean the same, all right? They all mean the same, but I treat them with PEEP or CPAP, right? 29-year-old man with no history of pulmonary dysfunction is admitted to the emergency department. Pure blood gases sample is drawn while the patient's breathing room air, and the following results are obtained. Okay, so this is like a real question, so I've got a list. I'm actually going to skip the list and go to the question. It says, in this situation, the patient's hypoxemia is most likely caused by. So I go back over here. Oops. Go back over here. I look at my CO2 and wow, I got a problem with ventilation. So that's my problem, ventilation with this guy. I'm not worried about the PO2 of 55. The poor ventilation is my problem because that's my first priority, right? My first life function I want to make sure is doing good. So I look over here at my answers and I'm looking for the thing that says bad ventilation. That's letter A. Okay, bad ventilation. That would be the correct answer. And then if I go to the next step and it's asking, I've got another patient here being admitted to the emergency department and they're breathing room air and the following results are obtained. Again, I've got a list. I'm going to skip, go to the question. It said, in this situation, the patient's hypoxemia is most likely caused by what? So I go back over here and I look at my CO2. Whoa, this CO2 is fine. So it's not a bad ventilation problem that's causing this. And what FiO2 did I say they were on? Room air. Is that right? Yeah, room air. So if it's not ventilation is not the problem, then the poor PO2 is going to be caused by VQ mismatching, right? Because those are the only two things. So where's my answer? That would be B, ventilation perfusion mismatch. Okay. Newborn infant with nasal flaring and retractions has the following blood gas results, breathing 60%. Once again, anything over 60% or 60% or greater, a bad PO2 means that's probably shunt, refractory hypoxemia, or venous admixture, right? And you fix it with pressure, PEEP or CPAP. I've got a list. I'm skipping the list. They want to know what I should recommend. So before I can recommend something, I've got to look at my blood gas. How are they ventilating? Well, they're ventilating fine, but the oxygenation is terrible and they're on 60%. So that means I've got a problem with what? Yes, refractory hypoxemia, shunting, or venous admixture, and I fix it with pressure, okay? So they want to know what I should do. And so I'm looking, here's a great one. 2 CPAPs, but this is an infant. Which type of CPAP should I give them? Well, infants need to be given mass CPAP. Okay, so that's kind of the style questions that you'll see interpreting on blood gases on the test. Now, this next, at the bottom of page 17 under acid-base balance, next to acid-base balance, you can write the word skip, okay? And you turn over to page 18. If they ask you something about acid-base balance or a metabolic problem, it's going to be number 2 in the middle of the page there, either a metabolic acidosis or alkalosis. Most everything on this test is going to be respiratory related. So it's either bad ventilation or too much ventilation, bad oxygenation or too much oxygenation. Okay. So you can kind of skip over 18 and 19 as long as you know how to diagnose a metabolic acidosis or alkalosis. On page 20, there are some special pathologies. These are exceptions to the rule for interpreting blood gases. So a couple things we're going to go over here, and then we'll be taking a break after we get through this part right here. Question? Tom must have got on accidentally. All right. So top of page 20, letter F, special pathologies, exceptions to the rule. Under number 1 there, I want you to highlight letter A, type 1, ABG looks good, the patient looks and feels bad. So this type 1 patient description, this is a Kettering thing. This is not something they're going to ask you on the test. What is a type 1 patient? This is just us in Kettering trying to help you understand what the exceptions are to the blood gas, okay? So the first type patient is the blood gas looks good, but the patient looks bad. And then the second type is the blood gas looks bad and the patient looks fine. Now, I tell you both of those things first because the thing we need to focus on is not the blood gas, we focus on the patient. So if I've got a patient that looks bad, but my blood gas says, hey, they're fine, I don't trust my blood gas. I always go by what my patient looks like, right? Same thing down here. If the blood gas looked bad, but the patient looks fine, then I got to go by what's going on with my patient. I got to do something. This blood gas, is not telling me really what's going on with the patient. All right. So some examples of type A patient is the CO poisoning, the anemia, the pulmonary embolus. Those are all examples of the patient looks bad. Or excuse me, the blood gas looks good, but the patient looks bad. And so, of course, in the CO poisoning, we got to put them on a high FiO2 and hyperbaric until we get the carboxyhemoglobin less than John's favorite number, 20, right? Okay. And then if it's anemia, we're going to give them blood. And then if it's a pulmonary embolus, we're going to give them clotting drugs. Okay. So as you look down through here on page 20, I want you to highlight under number 2 letters A and B. I've already told you all this stuff. I just kind of done it quickly. Letter C, remember we can't trust the saturation on a carbon monoxide poisoning patient, so we need a co-oximetry or hemoximetry. Letter D. Under number 3, anemia, highlight letter A and letter D. Under number 4, pulmonary embolus, highlight letter A. These are all potential risk factors or people that may get a pulmonary embolus, and then highlight letter B, C, D, E. And then letter F at the very bottom there is the medicines that we would give to prevent clots, like heparin, and then medicines that we would do to treat clots, like the streptokinase and the PTA or TPA. Okay. Top of page 21 is an example of number 5 is example of type 2 patient. This is a patient that looks bad, but the patient feels fine. So here again, excuse me, the blood gas looks bad, but the patient looks fine. So remember, COPD blood gases, the PCO2 is often high and the PO2 is often low, but yet they look pretty decent. They're not, chugging along unless you're sick for some reason. Okay. So on page 21, we give you a couple examples of that. Letter A is a blood gas showing there with the CO2 is at 62, so that's up, right? PO2 is 58, that's down, so we think we may need to ventilate this guy, but we need to look at that pH, and we see that pH is what? 36, so that's normal. So that would indicate that this guy's a CO2 retainer. And that's a pretty decent blood gas with a PO2 of 58 for a CO2 retainer, okay? We'll give you another example of one there with a patient on 40%. And what we're showing there is that in this example is that we're giving them too much oxygen. If you see that they're a COPD patient because they have elevated CO2 and they got a normal PO2, you know that's going to wipe out their drive to breathe. And that's why the pH is down. And we just go through a little checklist there to kind of show you or to remind you how to evaluate whether you're giving them too much oxygen or not. So you can kind of look at that. All right, on page 22, the oxygen dissociation curve, you can just write a big skip on that page. You don't have to worry about that. Again, we put all this information in here for completeness sake, but they're not going to ask any questions about it on the test. Okay. All right, so Tom, I got about almost 10 after. We got any questions or anything I need to go back over before we take a short break, a 10-minute break?
No, nothing at this point.
Well, I must be doing all right. Then either that or they're going to sleep. Hope they haven't done that. All right, so it is, why don't we come back about 20 minutes after the hour, and then we'll finish up this section, and we're going to be pretty much on schedule with where I need to be. So I'll see you back in about 10 minutes. Okay, I am back. And it's my understanding from Tom that he has tagged Kim as his replacement for the next little bit. And Kim, if you are monitoring, are there any questions or anything that I need to address before I move on into the pulmonary function stuff?
We'll have some that we're gonna do at the end of the day, if that's okay.
No problem. I
Okay.
appreciate that very much.
You're
Good to hear
welcome.
you.
You too.
All right. Thanks.
Yeah, you're welcome.
All right. So we're going to start on page 23. Pulmonary function testing. Again, the thing to remember about this section is that on this particular test, there's not going to be a lot of pulmonary function stuff because, again, they have two specialized tests for pulmonary functions. So they just want to see if you have the basic understanding of what PFTs are, okay? And when you would use them and how you would interpret basic values. All right, so the emphasis in on this test is going to be on spirometry. So that's what you got to be good at on the test is spirometry. So we'll start off first by talking about some of the different indications for testing. So this is important. This is kind of new on the test. So I would encourage you to highlight letter A there, the indications. We're going to identify and quantify changes. Number 2, we're going to evaluate and quantify therapy. And number 3, we're going to perform epidemiologic surveillance. And number 4, assess risk of complications. And number 5, determine disability. So those are the primary reasons we would get a pulmonary function. So that brings us now to our equipment. And again, you're not going to have to answer a lot of questions about the different types of equipment. You just have to know basically what the piece of equipment or the category of equipment does or what it measures. All right. So the first one here, these are things that measure volumes and flows. These are spirometers. Number 1, so highlight that. That's what they basically do, measure flows or volumes and flow rates. All right. Drop down to the bottom of page 23, the pneumatachometers. Those primarily measure flow, so highlight that. And letter B at the bottom is another example of a pneumatachometer, the flesh or the pressure differential pneumatachometer. It also measures flow and gives you a volume that registers there. Okay, top of page 24. Peak flow meters. Next to the word peak flow meters, I want you to write the word asthma. This is what we use to monitor asthma as to whether or not it's the patient is getting into trouble and how effective their medicines are working for them. Drop down the middle of page 24, number 5, how to measure the peak flow. You need to do letter E, blow out as hard and as fast as possible. And letter I, you need to record the highest of 3 numbers as a peak flow measurement. And then number 6, excuse me, letter A, the typical peak flow value is around 10 liters per second or 600 liters per minute. All right, that brings us to the top of page 25, the body box or the plethysmograph. Number 7, highlight that. Letter B, it measures thoracic gas volume, which is the same as functional residual capacity. Highlight letter D. The body plethysmograph should be calibrated prior to the procedure using the following, and we give you some information about that. Letter E, the quality control of the body plethysmograph. Highlight number 1 should be performed using an isothermal lung model. Number 2, the bottle is filled with a known volume of metal or wool that acts as a heat sink. Number 3, the practitioner sits in the box and attaches the lung model to the mouthpiece and then holds their breath while squeezing the bulb to simulate panting. Number 4, the volume measured should be plus or minus 5% of the volume of the lung model. And number 5, biological controls or healthy individuals can be used. The big thing to remember about the plethysmograph, it is the device that most accurately measures FRC and COPD patients. So out of all the devices that we use for monitoring pulmonary functions, this particular device is the most accurate. Top of page 26, number 8, the calibration and quality control of equipment. Highlight letter B, you're going to, volume calibration and leak tests are going to be done by using a large volume syringe, and its standard size is about 3 liters, which you see there in the illustration. Highlight letter C, the daily calibration with the 3-liter syringe should have an accuracy on the device that you're checking, should be plus or minus 3.5%. So it should be very close to 3 liters, as you can see the range there. Drop down to number 9, helium analyzer. Let you kind of read down through that. Number 10, the nitrogen analyzer, you kind of read down through that. On page 26, number 11, at the bottom of the page, the CO2, carbon monoxide, methane analyzers. This is something that's new on the test. I would highlight letter A, it uses infrared absorption. Letter B, there's a quick response for diffusion or DLCO measurement. And then the bottom of the page, letter G, along sample lines and moisture can adversely affect calibration and delay the response time. Top of page 27, the pressure measuring devices. Again, most of us are familiar with the blood pressure aneroid manometer. Down at the bottom of page 27, under number 13, MIP, MEP devices, letter A, under number 1, the MIP pressure, highlight letter A, is used to monitor and assess readiness to wean and ventilator patients. Letter B assesses the degree of muscle impairment in patients with Guillain-Barré and myasthenia gravis, and highlight letter C. Inspiratory pressures are described with negative numbers. And then at the very bottom of page 27 there, just above the illustration, highlight Roman numeral 5 there. Measurements of less than 20 centimeters indicate inspiratory muscle weakness. So you got to be better than 20, better than John's number, for it to be a good MIP. Top of page 28, number 2, the MEP, or maximum expiratory pressure, that can be helpful in evaluating a patient's ability to maintain an airway and clear secretions. And drop down to, again, under letter C, Roman numeral 5, measurements of less than 40 centimeters indicate poor ability to clear secretions. All right, less than 40, bad. Greater than 40, good. That brings us to the most important piece within this section, and that is spirometry. So here again, most of us are familiar with this illustration and understand that the over here, this would be an example of a patient's slow vital capacity being measured, and then on the left-hand side, relating the lung volumes and capacities to this graph. So just let me kind of go through the graph here real quickly with you just to kind of review, and then I'll show you the type of question that you may have on the test. So each one of these little tidal breaths, of course, are a tidal volume. And so this is in and out, and now the patient is taking a deep breath in and then exhaling all the way out as much as they can, and then going back to normal tidal breathing, just in and out here, okay? So as we correlate this graph to this information over here, we see we've already identified where the tidal volume is, and it's these waveforms, these smaller waveforms right here. But if you go above the top of the tidal volume all the way to the maximum inspiration, we refer to that as IRV, inspiratory reserve volume. And if we go below the tidal volume in the normal exhalation all the way down to the maximum expiration, we refer to that as expiratory residual volume. And then whatever volume that is left in the lung after a maximum expiration, we refer to that as residual volume. Okay, so knowing what these volumes are and where they are in relationship to the graphs here is very important. Now, we also need to know what the capacities or what volumes make up the capacities. And so that's why this illustration is so helpful, because you can see here the two volumes that make up inspiratory capacity are the IRV and the tidal volume. And then the ERV and the residual volume make up the functional residual capacity. And then the volumes that make up the vital capacity are, of course, the IRV, the tidal volume, and ERV. And then the volumes that, of course, make up the total lung capacity are IRV, tidal volume, ERV, and RV. So what would a question look like about this spirometry on the test? It would look something like what we've given you at the bottom of page 28. So here we've got the following information that's been reported to a patient. I've got a bunch of numbers I'm going to skip. They want to know what is the patient's vital capacity. Oh, okay. So I need to know what are the volumes that make up the vital capacity. Well, we just talked about that. The volumes that make up the vital capacity are IRV, tidal volume, and ERV. So what we do is we go over to the numbers they've given us here, and let's start totaling things up. So IRV is 3. The tidal volume is 0.5, so we got 3.5. And then the ERV is 1.5, so that is, say 3.5, 1.5, that's going to be 5, right? That would be correct. So that's how you would do that particular problem, right? Now, these next couple slides you don't have in the book. This is just some summary slides that I kind of put in here that one of the other instructors was using. I thought it might be helpful to some of you who kind of need the big picture before we start talking about interpretation of pulmonary functions. And so if you want to take a picture of these, feel free to do so. I'm going to, I would wait. There's several things I'm going to reveal to you. I'll tell you when is a good time to take the picture. But if you want to get your camera ready and be ready to take a screenshot, I'll let you know when everything's up on the slide so that you can get it all at one time. So here, the PFT thing to remember is just 2. There's just 2 things that pulmonary function is going to tell me. It's going to tell me whether I've got an obstructive problem or a restrictive problem as far as spirometry is concerned, all right? And so if I've got an obstructive problem, that means I'm going to have a problem with flow. If I've got a restrictive problem, that means I've got a problem with volume, all right? And the flows that typically I'm going to be looking at to evaluate obstruction is going to be the FEV1. That's going to be the primary one, all right? And then for restriction, I'm going to be looking at the vital capacity, all right? Now, the bottom thing down here tells me how I'm going to interpret this information. So if I've got an 80% of predicted on a particular vital capacity or FEV1, then I'm going to say that's normal. All right, that's good. If the pre and post bronchodilator has to be at least 12%, if it's at least 12%, then that's good. And then the other thing I need to look at is compare the FEV1 to FVC ratio. And if it's at least 70%, then that's considered to be good. So all of these numbers here are good. So if you want to go ahead and take a picture of this, that's everything that's on this particular slide. Feel free to do so. But it, like I said, it's just going to kind of give you an overview of what we're going to talk about in the next little bit as far as interpretation. All right. So top of page 29, let's talk about the slow vital capacity, number 2. Highlight number 2 there, letter A. You're going to tell the patient to take a deep breath in, and you're going to exhale out without force. So they're just going to kind of let the air out. All right. Letter B, the slow vital capacity will provide important volumes used for identifying restrictive defects, which we've already mentioned that. Under letter C there, highlight number 5, the vital capacity, of course, is equal to the IRV plus the tidal volume plus the ERV. We've already talked about that in our previous graph. Letter D, if we have decreased volumes, that's going to indicate restrictive lung disease. And letter E, a decreased vital capacity is the best indicator of restrictive lung disease. So those are a couple things for us to remember. All right. You've already got all that in your book. This next slide is a summary slide. You don't have this in your book. You may want to take a picture of it because this is just another way of looking at it. It's saying here, that if we have a normal vital capacity, we don't have any restriction. But if we have a vital capacity that is decreased, then that means we have a restrictive problem. And then we define what a decrease is. How much of a decrease? It has to be less than 80% of predicted. Okay? So feel free to take a shot of that if you'd like to. Then that brings us down to number 3 on the middle of page 29 there, forced vital capacity. Letter A, this again is a description when the patient takes in a deep breath as they can and then they blow out as hard and as fast as they can. Letter B, the patient instructed, well, I've already said that, letter B, sorry. Letter C, the FVC maneuver is the procedure that will provide important flow rates used to identify obstructive disease. So again, the FVC helps us get information about obstructive disease, all right? And as we're going to talk about here in just a second, under letter D, the following flows can be measured. We've already mentioned that. We've already got the graph there. Letter E at the very bottom there, on top of the graph, letter D, the FVC is not a flow. Remember that forced vital capacity is not a flow. It is a volume, and it should be equal to the slow vital capacity. So we can use this to talk about restriction. However, the forced vital capacity gives us all these flow rates. All these flow rates here are what we can use to figure out, do we have an obstructive problem? Okay? So there is also a summary slide here. Yes, at the top on page 30, highlight number 4, flow rates, letter A, forced expiratory volume in 1 second. This is the volume of gas that's expired in 1 second of the vital capacity. And if we have a decreased FEV1, it is a good indicator of obstructive disease. So highlight number 3 under letter A there at the top of the page, 30. All right. The next one we're going to talk about here, this is kind of a summary slide about how you can determine if it's an obstructive problem. Again, you don't have this in your book. So if you want to take a screenshot of it, feel free to do so. The FEV1 is normal, then it's not obstructive. If we have a decreased FEV1, then that's considered an obstructive. How much of a decrease? It has to be at least less than 80%. All right, that brings us to letter B, the FEV1 or FEV to FVC ratio, okay, or FEV percent. You can see there in the box, we have what the normal range should be for the FEV1 to FVC should be about 70%, so highlight that. Number 3, if we have a decreased FEV1 to FVC ratio, it's the best indicator for obstructive disease. All right. And then we give another little insight there, number 6. It says that if the FEV1 is decreased, but the FEV1 to FVC ratio is normal, then the patient has restrictive disease only. So in other words, if the FEV1 says you've got an obstruction, but the FEV1 to FVC ratio is within normal limits, at least 70%, then the FEV1 to FVC ratio trumps FEV1. So if you have to trust or try to figure out if the FEV1 is telling you one thing about obstruction, and the FEV1 to FVC ratio is telling you something else about obstruction, always go with the ratio. Right? The ratio trumps the FEV1 in terms of what's going on. Okay? That brings us to the middle of the page, 30, forced expiratory flow rate 200 to 1200. Here again, number 1, that's an average flow. The first 1,000 to 200 mils expired. You can highlight number 2. Decreased values are associated with large airway obstruction. Letter D, the 2575, Again, that's for small airways. And again, if there's a reduction of less than 80%, that would be considered abnormal. And then the peak expiratory flow rate, letter E, again, think about asthma. And the typical value for it should be about 10 liters per second or 600 liters per minute. All right. That brings us to the bottom of page 30. And this has to do with doing pre and post bronchodilator testing. Again, the reason we're doing this is to determine, is the obstruction reversible? Okay, so highlight number 1, or letter A under number 5. Letter B, the minimum increase is 12% and 200 mils. So we got to get at least 12% and 200 mils improvement in order to say the medicine's working. And then letter C, we need to hold all bronchodilator therapy for 8 hours prior to testing. And the bronchodilator we're going to use primarily is probably going to be albuterol, and we want to get 2.5 milligrams of that. Okay. Top of page 31, the flow volume loop, you may have to be able to interpret this and look at it and make some determinations about or how to read it. Okay. So let me just take a few minutes to show you how you would do that. Whoops, sorry. So basically this is flow on the vertical axis. This is volume on the horizontal axis. And so if we want to find out what the volume is the patient moved, like the vital capacity, we would start right here at the beginning, which is 0, okay? That's 0 on the curve. We'd come all the way down here. And then we'd come all the way down here. We see that's about 6 liters. That's how much volume was moved. So that's how you read the vital capacity, okay? So that's the first thing you got to be able to do. You may want to write that off to the left-hand side over here, read vital capacity, right? Next thing we got to be able to do is we got to be able to read the peak inspiratory flow rate. And so this side over here is the inspiratory flow going in down this direction. So to read peak inspiratory flow rate, we got to go to the very bottom of the graph, right here, and then come over to the flow scale and read it there. So that's about 4 liters per second. Okay, so that's the peak inspiratory flow rate. To read peak expiratory rate, that's the third thing that I've got to be able to do. So I got to first be able to read vital capacity. Second, got to be able to read PIF. We just did that one. Third one, I got to be able to read PEF, peak expiratory flow rate. So this is the expiratory side of the curve. So I go to the very top of it, come over here to the scale, and it's about 5.5 liters per second. All right. So just make sure you're able to read vital capacity, PIF, and PEF on the flow volume loop. The other thing about the loops is that their shapes can give us some insight into what may be going on with the lung condition. And so this would be considered a normal flow volume loop. Remember, all this little stuff right here in the center is just normal tidal breathing. And they come over here, take a deep breath in and blow out hard and fast, and it comes back around, and then take a deep breath back in, okay? So again, this is expiratory side, this is inspiratory side. So in this first one, this is a small airway obstruction. Again, any loop that has kind of a scooped out portion, that's going to be considered an airway obstruction. You see how this one here is a nice straight line, but this scooped out portion right here is indicating obstruction. This next one is restrictive defect because look how small the volume is. See, the amount of tidal or vital capacity is only about not even 1.5 liters, whereas the vital capacity here, going from here all the way to here, read down here, is about 7 liters. So that's a very small, that patient's not able to take a very deep breath at all. This over here is large airway obstruction. Again, with large airway obstruction, you can get some flows, but just not very high inspiratory and expiratory flows. So this flow is very low here. It's about 2 liters. This over here is about 2 liters also. Okay. So just know which shapes go with which problem. Is the main thing you need to know there. 32, interpretation of spirometry. Top of the page there, highlight letter D, under number 1, letter C. Predicted values are primarily based on age, height, and gender, and race and ethnicity. Okay. And then number 2, the classification of spirometry. This is from the ATS and ERS standards. So those are the people who set the guidelines for interpreting pulmonary functions. And this box is very important. Okay, so I would highlight the entire box, even though it's in a box and you already know it's important. I would highlight that entire box to make sure I know how to interpret pulmonary function. So any value on the pulmonary function on this test that's between 80 and 100%, that value is going to be considered normal. Any value that is 60 to 79% of predicted is going to be considered a mild disorder. And any value that's 40 to 59% is going to be considered a moderate disorder. And then any value that's less than 40% is going to be considered a severe disorder. And we give you some examples of how they would potentially present this information to interpret a pulmonary function on the test. All right. So let's look at the example down there below. So there's a lot of extra information in here that you really don't need to know. What we tell you at Kettering is what we want you to do is the first thing we want you to look at is we want you to look at that forced vital capacity. Okay. And ask yourself, is it greater than 80%? Is it normal? And in this case, of course, it's not. So if we've got a reduction in volume, that means we got a problem with restriction, right? And so this, 64, 65% of predicted values means that we've got a mild restrictive disorder here, okay? The next thing we want you to look at is we want you to focus in on the percent predicted of the FEV1. Well, it needs to be at least 80%. Well, that's more than 80%, so that will be considered normal. And so there's no problem with obstruction because, again, that's one of the key things we look at for obstruction is an FEV1. The last thing we want you to look at is the FEV1 to FVC ratio, okay, which is 96%. And again, it needs to be at least 70, right? So that's really good. So that's not a problem with obstruction. So in this particular pulmonary function, no obstruction problem because these two point towards obstruction. This points towards restriction. And so the problem here is a mild restrictive defect only. And that's what we tell you there at the bottom of page 32. That's the diagnosis. All right, let's try another one. Once again, the first thing we want you to look at is the forced vital capacity percent of predicted. Now, I'm not looking at any of these other numbers. I'm only looking at these percent predicted and the FEV1 FVC ratio. So that's above 80%, so that's normal. So there is no restriction. My next number I'm going to look at is the FEV1. Whoa, that's way down. That's way below 80%. That is down in the moderate range of our interpretation box, remember, okay? So I've got a moderate obstruction here. And then when I come down here to FEV1 to FVC, that's also a moderate obstruction. So the problem here is I don't have a restrictive problem, but I definitely have two things pointing at a moderate obstructive problem. And so that's how I would interpret that pulmonary function. Once again, I'm not looking at any of this other stuff. I'm only looking at these three things right here, okay? Keeping it simple. The next one is a little bit different. Here again, first thing we're going to look at is we're going to look at this guy's forced vital capacity. And again, we see that it's reduced. And so that means I've got a restrictive problem, right? Okay, because it's less than 80%. And this would be a severe, right? Severe restrictive problem because it's less than 40%. The FEV1 is also reduced, less than 80%, and this would also be considered to be a severe obstructive defect. Okay, so far I've got severe restrictive, severe obstructive. But when I look down here at my FEV1, it's within normal limits. Remember what I told you is that if the FEV1 says something's okay, and the FEV1 says no, there's an obstruction, which one are you going to believe? Well, the FEV1 to FVC ratio trumps the FEV1. So there is no obstruction, even though this says there is. This is the main one I'm going with. And so since there's no obstruction, the only problem this patient has is a severe restrictive lung defect. And that's what your answer tells you on page 33 there. Okay? So at the bottom of page 33 there, number 4, highlight number 4, remember the following. Patients can have any of the following combinations. You can have a restrictive only defect, which means all your volumes are decreased. B, they could have obstructive only, which means your flows are decreased. And then C, both obstructive and restrictive, you could have both your flows and volumes decreased. And then D, neither. So basically you'd have a normal PFT. Okay? Bottom of page 33, number 5, we give you a list of different types of obstructive and restrictive diseases. Letter A is the list of obstructive diseases, and we came up with a little acronym here called CBABE. And CBABE, what it stands for is cystic fibrosis, bronchitis, asthma, bronchiectasis, and emphysema. And so these are all the obstructive diseases that you may have on the test, the primary ones, okay? And so knowing that these are all obstructive means that they may respond to bronchodilator therapy, they may not, depends how severe it is. But everything else, if it's not a disease in the CBABE category here, then that's considered an obstructive, or excuse me, a restrictive defect. And so on top of page 34, we actually give you a list of restrictive diseases there, but notice that there's nobody in the CBABE group. Okay, so again, CBABE, all of those are obstructive. If it's not in the CBABE group, remember that's a restrictive defect, and that means that they got a reduction in lung volume. Okay. Under letter E there, quality assurance, drop down under number 1 to letter B as a forced vital capacity maneuver. Highlight letter 3. A minimum of 3 acceptable procedures should be recorded. And then number 4, the best test should be determined and used for reporting values. Okay, and we give you an example of how to do that there. On page 35, middle of the page there, letter F, additional pulmonary function tests that they may mention these on the test. You just need to know what they are and what they would indicate. The first one there is the maximum voluntary ventilation, or the MVV. Highlight letter A. Basically, this is when you're having the patient breathe hard and fast, deep and fast for as long as they possibly can. Highlight letter B, it should be performed for at least 10 to 12 to 15 seconds. And then you can extrapolate it out for a minute. And letter C, it's used to evaluate respiratory muscle reserve, endurance, or fatigue. And typically, if they're going for they're doing pre-op evaluation of patients for thoracic or abdominal surgery, then they'll do the MVV to kind of see what their actual pulmonary reserve is. So this is a test often done for thoracic and abdominal surgeries pre-operatively. All right, top of page 36, number 2, FRC measurement. This must be done in a lab, so this is not something that you can do at a bedside. Highlight letter A, you can use a helium dilution method. That's a closed method for measuring the residual volume and total lung capacity. Letter B, you could use the nitrogen washout or open method. Or letter C, you can use the plethysmograph method. Again, remember, the plethysmograph is going to be the most accurate. Okay. Highlight number 3 at the bottom there, gas diffusion capacity, or DLCO, letter A. That's what the name of the DLCO is, the carbon monoxide diffusion capacity. Highlight letter B, the normal values around 25. And then letter C, if you have a decreased DLCO, that means you have a decrease in diffusion. And patients that can have reduction in diffusion are oftentimes restrictive patients. And so you can see pulmonary fibrosis, sarcoid, ARDS, pulmonary edema numbers 1 through 3, those are all restrictive diseases. There's only one in the CBABE category, and that's emphysema. And remember, emphysema is destruction of the alveolar capillary membrane, and so that's why your diffusion is reduced. Top of page 37, letter D, quality control for the DLCO. This is new on the test. Highlight letter E. We'll actually read down through that and then go to letter E. Patient performance and standards include number 1, inspired volume should be greater than 90% on the slow vital capacity from spirometry. And number 2, breath hold time should be 10 seconds, the range of 8 to 12. Middle of the page 37, letter G, home testing. Many of the flow sensing spirometers have the capability to interface with portable computers, and you can use that to get your spirometry done at home. All right, so that's PFTs. That's not too bad. Just a little bit more to go here, and then we'll take a short break. So, top of page 38, let's talk about bronchoscopy. So, highlight letter B. Bronchoscopy can be performed for a diagnostic or therapeutic reasons, and we give you a box there to kind of give you the diagnostic examples and the therapeutic examples. But what I want you to do is I want you to add to that box. On the top of the diagnostic side, on the top of the box, I want you to write 2 words for me. Flexible best, flexible best. And then over on the therapeutic side, on top of it, I want you to write 2 words for me there. Rigid best, rigid best. So the flexible bronchoscope is best used for diagnostic things, and they've got them listed there. The rigid scope is better for therapeutic, and we have those things listed there. And so just basically in the box, what we've done is pretty much summarized everything in letter C there about the 2 different scopes, when you would use them, when you wouldn't use them, that kind of thing, okay, under 1 and 2. Highlight, you can highlight 1 and 2 if you'd like. Highlight number 3, the endobronchial ultrasound, or EBUS. This is something new on the test. This is letter B. It provides real-time ultrasound guidance for transbronchial needle aspiration. So it's kind of a tool that they're using to guide the interventionalist into the right spot to get the needle aspiration that they want of the tissue. And then number 4, the electromagnetic navigational bronchoscopy. This sounds like a bronchoscope with a GPS on it, doesn't it? Letter C, it's useful for obtaining biopsy samples from the peripheral pulmonary nodules. So again, it's used to navigate to the location of where you're trying to go to get a sample of the tissue that may be in question that you may be trying to rule out cancer for. The bottom of page 38, highlight letter D. You want to recommend flexible bronchoscope for intubating patients with a suspected neck fracture or any other difficult intubation, okay? Top of page 39, letter F, hazards and complications. Highlight number 1, the most common complication is mild epistaxis or nasal bleeding when the nasal route is used. Highlight number 3, if serious bleeding occurs, 1 or more of the following steps should be taken. Number 1, instill epinephrine, and that will cause vasoconstriction to stop the bleeding. Letter G, middle of the page, preparation for the procedure. Number 1, you want to A, check the patency of the scope lumen, B, check the light source, C, check the function of the optical fibers, letter D, check operation of video recording equipment, letter E, required equipment, of course, is going to be oxygen, suction, specimen collection equipment, and syringes for flush. Highlight number 2, patient preparation, letter A, administer local topical anesthetic. And you notice that all of those medicines they're listed there end in cane. So if you see a medicine that ends in cane, remember that's most likely a topical anesthetic. So lidocaine, benzocaine, acetacaine, novocaine, all of those are topical. The top of page 40, letter B, assemble the monitoring equipment, the pulse ox and the ECG. Letter C, you're going to administer a sedative. And notice that all those drugs that are listed there end in LAM or PAM. So remember, LAMs and PAMs are sedatives or relaxing or anti-anxiety drugs, however you want to say that. LAMs and PAMs are sedatives. They make you chill out, all right? Letter D, you may have to administer a narcotic. Morphine is the example we give you there for any analgesic or antitussive effects. Okay. Letter H, during the procedure, number one, the patient's response to the procedure should be monitored. Number two, you need to facilitate passage of the scope through the larynx. Patient should be instructed to breathe deep and slow. Number three, a sudden drop in heart rate could indicate a vagal response. Letter I there for patients receiving mechanical ventilation, you want to do number one, make sure that the endotracheal tube is at least 8.0. Number two, obtain a Bode adapter, and that's the picture of what you're looking at here, the illustration. Again, if you're not familiar with this device, this connects on the end of the ventilator circuit, and then this connects down here to the patient. And then when they get ready to insert the bronchoscope, they pull off this silicone sleeve and slide the bronchoscope down into the patient. And it helps prevent the patient from, minimizes hypoxemia, and also allows them to get ventilated during the procedure with the ventilator while they're doing that. Number three, administer a topical anesthetic through the tube. 4, you're going to increase the FiO2 to 100%. And then 5, you're going to increase the pressure alarm. That's what you do for patients on a mechanical ventilator. The following procedure, following the procedure, you're going to do number one, wipe the exterior surface of the scope with a soft cloth or brush. And then number 4, you're going to immerse the scope in an alkaline glutaraldehyde to disinfect. Okay? And that brings us to the end of pulmonary diagnostics. So we need to go back to question 16 in our pretest and answer a couple of these, and then we'll take a short break. Okay. Question 16. Which of the following values for oxygenation index, or OI, would indicate the need for ECMO in a newborn? We said it had to be at least if it was greater than 41, right? So the only number that's greater than 41 is this one right here, it's letter D. Question 17, a 44-year-old male has been admitted to the hospital after being involved in a skydiving accident. He was 6'4" tall and weighed 182 pounds. The patient has been orally intubated with an 8.5 tube. Chest radiograph reveals bilateral opacifications of all lung fields. Oh, that doesn't sound good. Mechanical ventilation has been established with a volume ventilator at the following settings. Okay, I've got a list. What am I going to do? That's right, I'm going to skip it. I've got another list. What am I going to do? That's right, I'm going to skip it. And then the question says, I'm going to find out what the question is. The patient's condition is most likely related to. So they want to know what's wrong. How do I find out what's wrong? I go back to my blood gas. The first thing I look at is what? My CO2. How's my CO2? It's at 43. So are they ventilating? Yes, they are. Next thing I look at is my PaO2, and it's at 45. Are they oxygenating? No, they are not. Again, what's the FiO2 that they're on? Oh, they're on 65%. And so that means the thing that's causing this oxygenation problem is what? That's right, shunting, venous admixture, or refractory hypoxemia, any of those three terms, okay? So that's what the problem is. Let's go and see if we can find it in the answer, okay? Well, some of you may have jumped on this one. Remember, PQ mismatching is this. That's not a shunt. This would be the only one in this list that would constitute the name of a shunt, venous admixture, okay? Now, what do we do to fix the problem for venous admixture or shunt or refractory hypoxemia? That's right, we do P per CPAP, correct. And again, the FiO2's got to be greater than 60% for us to interpret that as being the problem, right? Oh, great. Estimated shunt fraction for a patient with the following available data. Remember, shunt, that's our 3-step process for calculating this, all right? And the first thing we got to know is what is the AA gradient? So how many hundreds are there in the AA gradient here? Here's our steps, just in case you forgot. We're going to add 5% for each 100. So we got 2 100s in here. So that's going to be 5 times 2, which is going to be 10%, right? So that's our abnormal shunt, it's 10%. And then I got to add that abnormal shunt to my normal shunt. So 10 plus 5 is 15. So that's my answer. I'm looking for 15. Oh my goodness, they lied to me, Kevin. There's no 15. No, there's not 15, but this one right here is doggone close to it. 14, and I'm picking that one. That's the way I would do it. Okay. All right. We've got an 80 kilogram patient, post anesthesia unit following lower abdominal surgery, received mechanical ventilation. The following ventilator settings as follows. Again, I've got a list. I'm going to skip it. Blood gas, I'm going to skip that. The therapist should. They want to know what I should do. All right. So I'm going to go back over here and let's find out what the problem is. Look at the blood gas again. Before I look at that blood gas, so I want to look and remind myself what FiO2. Oh man, they're well over 60%. So if they've got an oxygenation problem, it's going to be either shunting, venous admixture, or refractory hypoxemia, right? And I'm going to do PEEP to fix that problem. So I come over here, I look at my CO2. That looks pretty good. I mean, it's less than 45, so that's okay. My PO2 is good. Oh, okay. No problem with oxygenation. And then I've got 7.35 up here. So again, no problem with acid-base balance. But so I'm sitting here thinking, well, everything looks good as far as the blood gas. Have they given me any other information? Well, the only other information they gave me is this right down here. Oh, what does that mean? AV difference. What does AV difference tell me about? Remember, I told you, anytime you see that V, that venous, you need to be thinking cardiac output. So what does this AV difference number tell me about this guy's cardiac output? Remember what normal AV difference is supposed to be? It's supposed to be 5 volumes percent. Okay? Remember, normal arterial difference or normal CaO2 is 20 volumes percent. Normal CVO2 is 15 volumes percent. And so 20 minus 15 is 5 volumes percent. So this is an elevated AV difference. Remember what we said? The AV difference has an indirect relationship with cardiac output. So if the AV difference goes up, that means cardiac output did what? Goes down. So I got a reduction in cardiac output. So I got a reduction in cardiac output. That means I must be using too much pressure to ventilate this patient, right? So I'm going to go back up here. They're on 15 of PEEP. So what I need to do here is I need to drop the level of PEEP because I'm impeding cardiac output, which is one of my life functions, and I don't want to do that. So I go back over here, and where's the answer that says reduce the PEEP? And there it is. Okay. You wouldn't want to reduce the FiO2 because the pH is good. The CO2 is good. You don't want to mess with it. And I've noticed they put in there maintain current settings because again, that would be something people would look at and well, my blood gas is fine, so I don't want to change anything. But anytime they give you something extra, take a close look at it and see if it tells you something else about what's going on with the patient. All right, just a word of caution there. Okay. Number 20, in preparation for the pulmonologist with the fiber optic bronchoscope for a 50-year-old woman receiving mechanical ventilation, the respiratory therapist notices the patient appears to be anxious about undergoing the procedure. Okay, so we need to relax this person. So the therapist should recommend administration of, well, which one of these is about sedation and relaxation? That's my lambs and Pams. All right, so where's my lamb and Pam? There he is right there. So that's the one I would pick. Okay. All right, so it's about 4:10. Let's come back about 4:20 for a break. And then before we leave on break, let me just check in here with Miss Kim to find out if there's any questions I need to address before we break.
Hey, John, there are actually 2.
Okay.
One they wanted to take a look at a slide again, and if I got the correct one, it was the summary on restrictive diseases.
Okay, is it the one that?
Probably not
that's
in their
part
book.
of
At the
our-
back. Go
is
ahead.
it part of our, or is it one of the extra ones that I stuck in there?
It's probably one of the extra ones, you know, if the vital capacity's decreased, means they're restrictive.
Okay, let me see.
If it's normal, yeah, it's back a ways, sorry.
Let's see. Come on, anytime.
That's all right. And then someone wants to go over the example on page D34 at the bottom.
Okay. So is it this one for the slow vital capacity summary? I mean, the
Yeah, I
restrictive
believe
one?
it is, yes.
Is it the restrictive disease summary or
Yes.
this one?
Yeah, that one I can't see, but hang on a second.
That
Yes, I
is
believe it's that one.
92.
Okay, yep, 92, yes.
All right. And then you said somebody wanted to go back over the example on page 34.
34 at the bottom of the page on the, well, it's the only example on that page.
Yeah, okay. So let's see, we really didn't talk about the example, but we will look at it. Let's see here. So this basically is looking at which one is the best. And remember the two things we told you about is it needs to have a minimum of 3 acceptable procedures should be recorded. So again, you see the 3 that are recorded there, and then you want to choose the best one as far as the vital capacity determined to use for the reporting results. All right. And so it says, it pretty much says, which is the best test, and it says trial 2. Okay. Because all of them are the best there. And then which one shows poor effort? That's trial 3. Because of the FEV1 is the lowest. Okay. And then the let's see, should the patient repeat the FVC? And it says yes. Okay, was there a specific question about that or?
They just wanted to go over the examples, they said.
Okay. Yeah, I didn't really go over those because it had all the
Sure, yeah.
down at the bottom there and everything. So hopefully that is
Okay.
helpful. Anything else?
Does someone want, are you gonna start mechanical vent after the break?
We are.
Okay, I just needed to know that.
Yep, we're going to do
Okay.
that. Probably go till about 5 or a little bit after. So, and then
Okay,
we'll have a
great.
question and answer period at the end there until 5:30.
Okay, all right, thanks,
Okay.
John.
All right,
Okay.
thank you. All right, I'll see you guys back at 4:20.
No, all steps so far, John.
Great, perfect. Thank you, Kim.
You're welcome.
All right, so we're going to start in mechanical ventilation here, section E. We're just going to get just barely touch the beginning of it, but if we get a little bit of a head start here today, that'll make things go a little bit easier tomorrow for you, I think. So a couple things I'd like to point out about the mechanical ventilation on the TMC exam. You may want to make a list of these at the top of page of the mechanical ventilation section, section E. First of all, there's going to be a lot of questions related to mechanical ventilation, because that's one of the most difficult things we have to do as respiratory therapists. They're not going to talk a lot about brands. It's more about the concepts of mechanical ventilation and, you know, when you go up on rate or tidal volume and so on and so forth. The other thing is that there tends to be a little bit of a lag behind current clinical practice. So, you know, what you may be seeing happening in the units right now, some of that may not actually be appearing on the test. So you have to kind of keep an open mind about this section of mechanical ventilation. It tends to be pretty generic. And again, the test matrix is what we use as our guide to what we include in this section and what we use to evaluate what's most important. So this is really more about the approach to mechanical ventilation. And what I find interesting is that a lot of people, whenever they look at the chapter on mechanical ventilation and the amount of time that we spend on it, they're kind of surprised because, you know, most people, that's what they want. They want to learn a lot about mechanical ventilation. I think the test is full of mechanical ventilation, and it is, but here's the thing. If you don't know what's wrong, you're not going to know how to fix it. And so here again, you've got to be good at patient assessment. And so patient assessment is the foundational element that I think helps you really the most on this test. Knowing, you know, about mechanical ventilation, how to pick settings and things like that, that's also very helpful. But the patient assessment piece is the piece that's really going to give you the most bang for your buck in terms of being able to answer more questions. Because if you're weak in patient assessment, you will not do good on this exam. That's just a fact. So you got to be able to figure out what's wrong and then be able to determine what to do to fix it. Okay. So if you turn over to page E3, this is the outline there. We're going to talk briefly about mechanical ventilation terminology. We'll talk about equipment, and then we'll get into clinical application of mechanical ventilation. And when we get into clinical application of mechanical ventilation, we at Kettering do that by using these three phases. Phase 1 is initiating mechanical ventilation. Phase 2 is caring for the patient receiving mechanical ventilation. And phase 3 is weaning or liberation from mechanical ventilation. So when you hear us talking about phase 1 mechanical ventilation, phase 2 mechanical ventilation, that is a Kettering term. That's not something they're going to talk about on the test, okay? But we do it that way so it kind of helps break up and kind of give you the parameters behind what you need to be thinking about when you're in that phase, okay? So it's kind of a teaching tool that we use to kind of organize our study guide materials so that you know, okay, these are things I need to be thinking about if I'm in phase 1, 2, or 3, all right? And then the last thing we'll talk about will be positive pressure. Now, we won't, like I said, won't be able to get through all of this today, but I wanted to get just a little bit of a head start to kind of, so we'll have a little bit of breathing room tomorrow to get through everything we need to get through, okay? So starting on page 4, let's talk about terminology. Under Roman numeral 1 there, letter A, there are 4 primary variables during positive pressure mechanical ventilation, and those are listed there for you. Trigger variability, 2, control or target variability, 3, limit variability, and 4, cycling variability. And we'll talk about each of these individually here in just a little bit. So starting under letter B there, let's talk about trigger variability. This is the parameter on the ventilator that starts the breath, the positive pressure breath, okay? And there's a number of ways that that can be triggered. You can see there, number 1, it can be pressure triggered. Number 2, it can be flow triggered. Number 3, it can be volume triggered. Number 4, again, time triggered. Number 5, manual triggered. So those are all ways that we can actually trigger or start the breath. But the thing I want you to notice is that numbers 1, 2, and 3, those are triggered by the patient, all right? So a patient has to be spontaneously breathing in order for those particular trigger variables to be used. And then number 4, the time trigger, that's basically done by the ventilator. So you may want to put vent beside number 4. And then, of course, number 5, the manual trigger, that's when you go up and say, hey, I want this patient to get a breath. All right, so the big thing to keep in mind here is who's triggering the ventilator? Is it the patient, is it you, or is it the ventilator doing the triggering? All right, so kind of keep that in perspective as you think about that variable. Letter C, the control or target variable. This is the primary variable that the ventilator adjusts to achieve inspiration. Highlight number 1, it could be the volume control, or number 2, it could be pressure control. So here again, this is the way I like to explain it is who's king? Is volume king or is pressure king? You know, what are we trying to do? We want to focus on pressure, we want to focus on volume. And you have to decide, you know, which way you're going to approach that particular patient situation, which one's going to be better for them. All right. Top of page 5 is the limit variable. Highlight number 1. This is basically establishes a maximum value for that particular variable, whether it's pressure, volume, time, or flow. And then number 3, doesn't matter which variable it is, but it doesn't end inspiration. It just creates a plateau or a pressure hold on the breath. And you can see that illustrated down here in the ventilator graphic. Okay. Top of page 6, letter E, cycling variable. This is the variable that ends or terminates the inspiratory phase of a positive pressure breath. Highlight number 1, the volume cycled. This is the most common way that the breath is terminated. Under number 1 there, highlight letter C. The advantage of this is that the minute volume can remain constant and provide stable blood gases. Then highlight letter D. The airway pressure will increase or decrease with changes in the patient's compliance and or airway resistance. And then letter G, the disadvantage to this is that as lung compliance or airway resistance gets worse, and you can tell that by looking at the PIP and the plateau, both of those go up, number 1 under G there, it could too result in barrel or volume trauma. All right, so it's basically determining, hey, the volume is what we're looking to give, and we don't care where the pressure goes. So you got to watch the pressure, make sure you don't, you know, cause the barrel or the volume trauma. The second example there is pressure cycled, and next to pressure cycled, I want you to write 4 letters. IPPB. IPPB. Those IPPB is basically, that's what this type of ventilation is, okay? And so highlight letter B, although the pressure is going to remain constant, all right, the volume can change depending upon the patient's lung compliance or airway resistance. So again, you have to monitor the volume on this much more carefully because there's the potential for hypoventilating the patient, not giving them enough volume because of the change in their lung characteristics. Number 3 there, time cycled. Highlight letter D, it's used as a cycling variable during pressure control ventilation. And then number 4, the flow cycled. Highlight letter A, this is positive pressure applied to the airway until a predetermined flow is achieved. And letter C, this is the normal cycling mechanism for turning the breath off in positive and pressure support ventilation. Okay. Now, bottom of page 6, there's several different types of breaths. There's the spontaneous breath, where that's basically where the patient does everything. The mandatory breath, that means that the ventilator does everything. And then you have one down here that's called the assisted breath. That's where you get help from the patient and the machine. Both of them are controlling certain elements of the breath as it's delivered. All right, that brings us over to the top of page 7, ventilator circuits. And the middle of the page there, now highlight number 2, changing ventilator circuits. This is on the MBRC exam. These are times when you would change the circuit. All right, no matter what you're used to doing at your hospital, this is what you want to follow on the test. So letter A, ventilator circuit should not be changed on a regular basis unless 1, their circuit is grossly contaminated, or 2, there's a malfunction, such as a leak. The other thing you need to remember about changing ventilator circuits at the MBRC is letter C, that manual ventilation is going to, with a resuscitation bag, will be necessary while the new circuit is attached and tested by another person. So at the MBRC hospital, it takes 2 people to change a ventilator circuit. I know you may be able to do it with one hand tied behind your back, but if on the test, if they ask you about gathering equipment and support to do a ventilator change, and they offer you a human body or a nurse or somebody to assist, always make sure you choose that. All right? And that way you've got somebody that can provide ventilation while you're going through the process of changing the circuit out and checking it to make sure it's working properly. Bottom of page 7, ventilator alarms. Number 1, common alarms, highlight letter A. The high pressure alarm should be set about 10 centimeters above peak airway pressure. Again, this is where they want you to set your alarms at the MBRC hospital. Letter B, minimum exhaled volume is set to about 100 mils below the exhaled tidal volume. And letter C, the low pressure alarm is going to be set 10 centimeters below the peak airway pressure. All right. As far as troubleshooting, top of page 8, you're always going to provide manual ventilation first. Remember, manual or ventilation is the most important life function. All right. Under number 2 at the top of page 8, highlight letter A, the low pressure alarm. You want to consider number 2, a leak in the ventilator circuit, or number 3, insufficient flow. Of course, a patient disconnect could be also, but that's typically not one they're going to throw in there at you. Letter B, the high pressure alarm. Number 1, you want to consider patient obstruction, so make sure you can pass a catheter through that, make sure the tube's not obstructed, or the patient hasn't rolled over on the tube and kinked it off. Number 2, equipment obstruction. Again, that would be the ventilator circuit. Letter C, if you get a low exhale volume alarm, you want to again consider possible disconnect, low spontaneous tidal volume. And then we give you an example of what that may look like there. Okay. You don't necessarily need to worry about the rest of that down below. We just tell people you strike down from D where it says temperature alarm down. They don't typically ask too many things about that. All right, that brings us to top of page 9, clinical application of mechanical ventilation. Remember, we mentioned that there were 3 phases that we use for our teaching methodology. Phase 1 is whenever you put the patient on the ventilator. Phase 2 is when the patient is on the ventilator, but usually something goes wrong and you got to fix it. And then phase 3 is when the patient has been assessed and evaluated and determined that it's time for them to come off the ventilator. All right. So those are the 3 Kettering phases that we're going to be talking about here. So we're going to start off with phase 1. So phase 1, indications for mechanical ventilation. Just like with everything else on this test, you absolutely have to know when you would use a particular therapeutic modality. And it's no different for mechanical ventilation. So we have them listed there for you. Number 1, apnea would be one, of course, that's an absolute indication. And then number 2, the acute ventilatory failure. Number 3, impending ventilatory failure, which means that you got a trend or rising in your CO2. And then number 4, you've got a problem with oxygenation. So, if they're not ventilating, maybe you need to do something to reduce the work of breathing to help with their PaO2. Highlight letter B at the bottom there, patient assessment, clinical lab. You need to assess the blood gas. The thing I want you to highlight there is the CO2 row, 35 to 45. That's how you know that whether or not they need a ventilator, that 35 to 45, right? Just like we talked about in our blood gases. We go over to page 10, and I don't know if you saw that. I'm going to back it up and watch it. You see how I made that table spin on my screen? That's supposed to try to get your attention. This is important information here. Again, this is a box that is very, very important. And if you know this box, and I'm talking specifically about this stuff that I have in the acceptable column, the highlighted area, if you know those numbers, then you're going to know when it's time to put somebody on a ventilator, even without a blood gas. And you got to be able to do that on this test. You can't just rely on blood gases to decide whether or not you're going to put the patient on the ventilator. All right. So as you look at these, you can see that the body capacity has to be greater than 10 mils per kilogram, or double the tidal volume. MIP, we've already mentioned, is greater than John's number of 20. Respiratory rate 8 to 20. Spontaneous tidal volume 5 mils, greater than 5 mils per kilogram. And minute ventilation less than 10 liters per minute. And then the MEP should be around 40. So anything less than these values is what's considered unacceptable. So all these things over here are less than what's in this box, right? So if you don't get at least that, then you're going to have a problem. Okay? So make sure that you think about, make sure you know this middle acceptable column here. All right? Now, the one at the bottom of 10 is also important. Again, these are physiologic assessment calculations about the need for mechanical ventilation. And again, make sure you know this column right here that I've got highlighted. If they've got a VD to VT less than 60, they don't need a ventilator. And the other one I would highlight would be this shunt. If the shunt is less than John's favorite number, 20%, they don't need a ventilator. But over here, you can see that greater than 60, less than or greater than 20, that means that those are unacceptable and they need to be on a mechanical ventilator. Top of page 11, initial ventilator settings. Notice there on the screen it says that any mode is acceptable in phase 1, and that is highlighted there in letter A. Okay, so any mode is acceptable for initial setup. And letter B, do not rule out an option because of mode. So if we're in phase 1 where we're trying to decide, does the patient need to be put on a ventilator, then we don't concern ourselves with what mode we put them in. What we concern ourselves with are the initial settings. All right, initial settings is what we're looking for. So how do we know what our initial setting should be? Well, that's in the next box in the middle of the page there. Notice again, I had it flipping around and making all kinds of movement, meaning that this is very important. Here again, this is another box that if you want to be successful on the MBRC exam, you've got to know this box backwards and forwards, all right? Because it gives you guidance on how you select your initial ventilator settings. And that's usually the hardest part. A lot of people, they're sitting there thinking they're not sure where to start or if they should start on ventilation, okay? So let's walk through this and I'll show you how you would do this. Okay, and we'll have a couple of examples to practice here before we wrap up for the day. So the tidal volume, the way you're going to determine tidal volume for all patients on this test, you're going to do a range of 5 to 10 mils per kilogram of ideal body weight. That's going to be the range for your tidal volume. You're always going to pick tidal volume first, okay? And I'll show you how to do this here in just a minute. The pressure can, if you decide that you're going to ventilate the patient by pressure, then what we're going to do is make sure that the pressure is less than 35 centimeters of water. All right. So again, remember, we can either volume ventilate them or pressure ventilate them. And so you're going to figure out exactly what those values are for each one of these, okay? So here we'll have to do some calculations. This one is just a straight number. We want to make it less than 35 centimeters of water. The respiratory rate, we want them in a range between 10 to 20. The FiO2, if their patient is on room air, then we're going to start them off on that range like we said in our oxygenation box, somewhere between 40 to 60%. If they're already on oxygen, when we put them on the ventilator, we'll put them on the same level of oxygen, all right? Same level. PEEP, if we don't have any prior information, we'll start them off on 2 to 6. And if they're on CPAP, then we'll basically start them off on that level of pressure when we put them on the ventilator. Okay? Now, based upon that, let's go down to the bottom of page 11 there under letter A, and let's review how we want you to calculate the ideal body weight. I know that there's a number of different ways that you can do that, but what we're recommending is this one way, and you do it for both the female and male patients, okay? So let's take a look at that. So the way you're going to calculate ideal body weight is you're going to take the inches that are over 5 feet and you're going to double them. All right, I'll show you here in just a minute. And then you're just going to add 50 kilograms to that, and that will give you your ideal weight. So we give you a couple of examples here. Look at number 2. Here we've got a male who's 5'10", 5 foot 10 inches tall. So the number of inches over 5 feet is 10. All right, we're going to double that. Oops, back up. Here we go. So we're going to double that. So 2 times 10 is 20. And then we're going to take that 20 and we're going to add it to 50. And so 50 plus 20 is 70 kilograms. Right? So that's what this guy's ideal weight is. To do a female, if she's 5'4", again, 4 inches over 5 feet. So we're going to take the 4 inches and double it. That's going to give us 8. Right? And then we're going to take that 8 and we're going to add it to the 50. That'll give us 58 kilograms. So that's the thing we want to remember is how to calculate our ideal body weight. Now, once we've done that, all right, you don't have this slide in your book. So if you want to take a picture of this or a screenshot, feel free to do so. This is just kind of the steps of how we would go through and estimate the tidal volume range for a particular patient, okay? So the first thing we have to do is we have to look at the ideal weight, okay, in kilograms, and then multiply that by 10, because our range for this is 5 to 10 milliliters per kilogram, right? So again, the upper limit is going to be the ideal body weight times 10, all right? That's the upper limit. And so in this example, we just had the 70 kilogram man multiplied times 10, that's going to give us our upper tidal volume of 700 cc's. That's our upper limit tidal volume. And then to find out the lower limit tidal volume, all we're going to do is we're going to cut this number in half. So it says here, it says cut the tidal volume limit in half, and that's going to give us our lower tidal volume limit. So I take the 700, divide it by 2, cut it in half, that's 350 cc's. Okay, that's the lower limit. And so our tidal volume range looks like this for this patient of 70 kilograms. 350 cc's on my lower end, up to 700 cc's on my upper end. All right. Now, I know what some of you are saying. Well, they told us in school we have to do it by 8. And I understand that, but I'm telling you, for this test, if you will use this 5 to 10 range, it makes the math easier. It makes it easier to check, make sure you got something right. And not only that, but you can use it also for helping you to determine what the vital capacity and spontaneous tidal volume mechanics should be. I'll show you how to do that tomorrow, okay? But it's pretty simple. You just have to know what their body weight is. And again, if they're not overweight, then you don't have to calculate the ideal body weight. But if you know what the ideal body weight is, then just multiply that times 10. That's going to give you your upper range tidal volume, okay? And then that cut that in half, that gives you a lower range. And once I've got this range, what I'm going to do, the answer that I'm looking for on the test is not up here at the high end where I know you want to stay away from. I'm looking for something in the middle. So you want to choose a tidal volume that is close to the middle of the range. So for this particular range here, I'm looking at somewhere around 500 to 600, okay, for this guy's tidal volume to start them off, all right? And so that's how you would walk through the steps of calculating an actual tidal volume, okay? Now, I've got some examples here. Oh, let me make one other comment. On the bottom of page 11, highlight letter B. Remember that for severe asthma patients, you're going to recommend an initial tidal volume of 5 mils per kilogram. But let me show you something here. Less than 4 milliliters per kilogram. So again, I don't even remember, I don't ever think about B whenever I'm taking the test, because if I'm doing 5 to 10, I'm already down here at the low end. Again, so if I'm thinking about an asthma patient, this is 5. I already know this is 5 mils per kilogram. So I just need to go a little bit less than that for an appropriate tidal volume for them if they're asthmatic, okay? So again, I don't remember all these other small ranges or whatever that they are like this exception to the rule. I just stick with that one rule, 5 to 10 mils per kilogram, which is back over here, right here. I always stick with this, 5 to 10. That's what I calculate all my tidal volumes on. And so if I'm doing it for an asthmatic or COPD patient or trying to minimize the amount of tidal volume I give them, then I choose the lower tidal volume, look at the lower tidal volume and find something a little bit less than that. That's how I do it. Okay. All right. So let's do a couple examples of these and then we'll stop for the day. Okay. So here's the first one, top of page 12. We've got a 23-year-old female. She's 5'6", weighs 132 pounds. Now I can look at that and say, you know, she's not overweight. You may not be able to do that. And so you may want to have to go through the process of calculating the ideal weight, which we'll do here in just a minute. Admitted to the ED for following drug overdose. Her arterial blood gas is on room air as follows. Now again, I'm not doing any calculations or anything until I see what the question is. So I come down here, I've got a list, I'm going to skip it. It says here that the physician has written orders for intubation and mechanical ventilation. Which of the following are most appropriate? So I'm in phase 1 and I'm using my box, my parameter box there on page 11. That's what I'm going to use to pick my settings. Okay, so I'm going to go down here and look at the situation for my vent settings. I'm going to initially calculate my ideal weight. I could use 60 kilograms since she's not overweight, but if I want to calculate the ideal weight just for practice, again, I'm taking the inches over 6 feet, doubling it. That's going to be 12, right? And then 12 plus 50 is going to be 62. So that's my ideal weight there. So it's pretty close to what her actual weight is. So really, I could use either one of these for doing my range, all right? Next thing I'm going to do is calculate my tidal volume. I'm going to do that by doing this down here. I'm going to take the 60 kilograms, all right, multiply it times 10. That's 600 cc's. That's my upper tidal volume range. And then my 600 cc's, I'm going to cut it in half to get my lower range. And then I'm going to look towards the middle, somewhere around 450. Okay, so that's kind of where I get this tidal volume calculation from here. Okay, so once I got the range, I know I'm shooting for something in the middle here. Now, if they don't give me the option to ventilate them with tidal volume and they say ventilate with pressure, then I'm going to do something less than 35. That's what I'm going to choose. Okay. The rate for my box says I should choose 10 to 20. So that's going to, and for every patient that I put on mechanical ventilation, I do all these calculations every time on a separate piece of paper so I've got something to look at, all right? 40% to 60% is the range I'll pick for the FiO2. And then the PEEP range, since they're not on PEEP, 2 to 6, that's what I would pick, all right? So now I go over here to my options. And what I've done is, because I've written all this down on my piece of paper, got my tidal volume range, I got my PIP range, I got my frequency range, I got my FiO2 range, and I got my PEEP range. Now it's going to be very easy for me to find the right answer. And this is how I'm going to do it. So you just watch me as I go through this. I start off with the very first one, and I ask myself, can I use this tidal volume? Well, yeah, it's within my range. I could use that tidal volume. Could I use this rate? No, it's less than 10, so I can't use this answer. Could I use this tidal volume? Yeah, that's in my range. I could use that. Could I use this respiratory rate? No, I couldn't, so I'm not going to pick B. Could I do a tidal volume of 500? Well, yeah, that's in my range. Could I do a rate of 14? That's in my range, yes. Could I do 65%? No, that's too high for my FiO2. I can't use that. So I'm not going to pick C. Could I do 600? Yeah, and again, I know some of you are saying, whoa, man, that's really high tidal volume. But again, this is the only answer, as you'll see here. That is in my range. Could I do that rate? Yes, I could do that. Could I do that FiO2? Yes, I could do that. Could I do that PEEP? And so basically, this is the only answer that has everything that's within the ranges that I've given you. All right? And so that's going to be the right answer. Okay? That's how you would pick the right answer. All right, let's do one more. Here we've got 4 days following a splenectomy, 63-year-old male. He is 5'8", 154 pounds. Again, I'm looking at that. I know he's not overweight. So I could use the actual weight if I need to or calculate. But I always ask myself, when they give a weight, I always ask myself the question, are they overweight? And if I can't answer it, then I know that if I have to calculate a tidal volume, I need to use ideal weight. Following blood gas results have been given on CPAP of 10 and an FiO2 of 40%. I've got a list. I'm going to skip it. And they want me to do what? Yeah, okay, they haven't answered that. Let me go back through here first. So the question is, the physician has written orders for intubation mechanical ventilation, which of the following the most appropriate? So to come up with that, I'm going to go back over here and I'm going to do my calculation. So the first calculation is going to be my tidal volume, or excuse me, my ideal weight. So again, I could have used the 70 kilograms, the actual weight, or I could have calculated. And so the number of inches over 5 feet was 10. 10 times 2 is 20, plus 50 is 70. So you can see the ideal weight and the actual weight are the same, okay? I'm going to use that to calculate my tidal volume range. So I take the 70 kilograms, multiply it times 10, that gives me the 700. Okay, that's my upper range tidal volume here. I'm going to take that 700, I'm going to cut it in half. That's going to give me 350 cc's. All right, that's going to be my lower tidal volume range. All right, so there's my tidal volume range, 350 to 700. And I'll look towards the middle, which would be right around 525 cc. So around 500 cc would be in the middle of it, okay? The PIP, I would want it less than 35, okay? And then the frequency would be 10 to 20. The FiO2 is going to be 40% because that's the FiO2 that they're on right now. And then the PEEP would be 10 because they're on a CPAP of 10, all right? So those are the answers that I'm looking for in my settings, or the ranges, all right? So I've got my piece of paper here with all of those things written down. So now it becomes very easy for me to figure out what I'm going to do. Start off with the very first one, letter A. And notice how I haven't even looked at or paid any attention to the modes. I'm only looking at tidal volume and pressure initially, then going to frequency, then going to FiO2, then going to PEEP. All right. And so don't get hung up on modes. That's my point here. So the PIP is 50. Could I use a pressure of 50 to ventilate this patient? Well, the max it says here is 35. So I cannot use that. So I can't use this answer at all. Could I use a PIP of 30? Well, absolutely. I could use a PIP of 30. Could I do a frequency of 12? Yeah, that's between 10 and 20. Could I do an FiO2 of 40%? Yeah, that's what I'm on. Could I do PEEP of 10? And yes, that would be correct. So this would be the one that I would pick, and it would be right. Well, let's just go on and for practice, look at these again. Could I do 25? Yeah, I could do 25. Could I do a rate of 26? No, that's too high, right? Could I do a PIP of 40? No, that's over 35. So here again, you see the best answer is this one that I chose here based upon these ranges. Okay? All right. How about some homework? So same homework as last night. If at all possible, go home and do absolutely nothing. All right? Take it easy. Because you'll need that tomorrow when you come in first thing in the morning, or first part of the day there, to work through this. What I would say is that, like I said, if people that end up going through and looking more at this stuff tomorrow, they're just not very fresh, and it just doesn't work out very good. So make sure that tomorrow we're going to start at 11 a.m. Eastern Daylight Savings Time. Make sure you bring your clinical sim lecture book or have that with you, and the practice problem book, because we'll start in those tomorrow in addition to finishing up our study guide. If what I'm going to do is Kim and I are going to kind of stick around for just a little bit to see if there's actually any questions that we need to answer. If you don't have any questions for us and you want to go ahead and check out of the seminar, that's absolutely fine. We will talk with you tomorrow. And what I will do is, I guess I'm going to go ahead and unmic unless Kim has already done that. Let's see. Did I do that? Oh, here we go. Let's see. Yes. Okay, so I think I've got everybody unmuted. If anybody has a question that they want to ask verbally, I'll let you kind of chime in there to ask the question. Just try not to step on each other. And the other thing is, if you don't feel comfortable doing that, you just want to type it and send it to Kim through the chat, that's fine. She can either answer it or she can defer it to me. If I'm trying to think here. Oh, the other thing is, if you feel uncomfortable asking questions in either of these two formats and you'd rather just either text me or give me a call on the phone after we kind of shut the webinar down, I'd be happy to talk with you, over the phone or through text. So what we got, Kim?
Well, Kim is gone. You got Tom back again.
Tom is back. Oh my goodness.
Okay. First one is related to how we calculate tidal volume, and I'll just read it.
Okay.
Are we not going to use 6 to 8 mLs per kilogram for IDW? I'm not sure what that is. Are we not going to use 45 for the conversion factor for females?
And the answer to that is no. And the reason why is because, like I said, if you'll do the 5 to 10, the math is easier. It's easier to check your work. And again, if you go between the 5 mils to 10 mils kilograms and then shoot for a tidal volume in your answer that's closer to the middle, all right, you'll be fine on the test. Okay. And you won't have any problems with I mean, I actually did this with for the continuing education questions that we have to do for our maintaining our competency for the MBRC. They had a question on there, and I took this. I didn't even study for the thing. I just kind of did it based the way we teach people to do it here, and it worked out fine. So that's been my experience. I don't know, Tom, did you have something you wanted to? Did you have
No, I
different than that?
agree with you completely. Couple of comments. First is there's about 6 different ways to do ideal body weight.
Oh, yeah.
If you have a way that you're comfortable with and you want to keep doing it, be my guest. We just give you another
Absolutely.
option.
That's right. That's
And the
right.
second thing is, if you want to use 6 to 8 mLs per kilogram, go ahead, be my guest. I think
Yes.
what you're going to find when we get to the practice simulations, for example, that even though you might be using a different formula for ideal body weight and you're using 6 to 8 mLs per kilo, we're still picking the same answers out of the
Right.
list they give us. So
Yeah.
remember that we are consultants. We're here to give you advice. It's kind of up to you to decide if you want to take our advice or you want to do it your way. So,
That's right. I agree.
the second one was if you could quickly go back to the study guide and on pages D as in dog 11 through 13, just quickly tell us what needs to be highlighted.
D13 through what?
D is in dog 11 through D is in dog 13, just those 3 pages.
Okay. All right. So I'll do that real quick here. That's under the calculation. So yeah, number 1, under number 1, letter D, letter E. Under number 2, letters E, letter F in the box. D12, number 3, letters E, F, and G. Number 4, letters C and D, and letter E. Number 5, letter D, E, F, G, and H. Number 6 on page 12, letter C and F. And on page 13, D13, number 7, letters B, letters C, and letters D. Just do 13, right?
Yes.
Okay.
And then while you're on a roll there, also in the same chapter, section D is in dog, pages 34 and 35.
34 and 35. Okay, so top of page 34, highlight letter B. Drop down under letter E, their quality assurance, down to letter B, middle of the page, number 3, number 4. On page 35, letter F, number 1, letter A, letter B, and letter C.
Okay. Whoops, here we go. All right, can you go back to the last example again on page E as in Edward 12? That's going to be the 63-year-old dude who had to have his spleen out.
You said letter D.
E as in Edward.
E is in Edward.
It was the calculation of vent settings for the second example.
All right.
Yeah, you have a slide for that one. There you go.
It's the first one.
That's it. Second one. She said the last example. There's only 2,
Oh,
so I'm
Oh
thinking
yeah,
it's
this
letter
is
B. Yeah, 4 days follow it. That's it.
okay. All right. So what do they want? What do they want? To go back over
if
it?
you could go, it says go back. So if you could just kind of explain again how you pick the vent settings.
Okay. So what I did here, again, we know that we want vent settings. So the next thing is to select tidal volume, or actually we got to know our ideal body weight. So I have to do that first. Either that or select if I know that they're not overweight, then I won't worry about doing the ideal body weight. I'll just use their actual. But if you're not sure, then the safe bet is just to go ahead and calculate ideal body weight. And again, however you want to do that, this is, for me, it's pretty easy because there's only one formula for both male and female.
Okay, now, John, for this example, he's 5'8".
Oh, is he
So that would
5'8"?
be 2 times 8, right?
Yeah. Sorry
So
about
it'd
that.
be 16, so he'd be 66 kilos instead of 70, which doesn't make a difference.
Yeah, so this is supposed to be 8, right?
Yeah. In the first one, I think she was, yeah.
Yeah, so one's 5'6" and the other one is 5'8". Sorry about that. Okay.
That's okay. I think that may be where a couple of them got a little messed up.
You're absolutely right. I would be messed up too. Hang on just a second. Let me get this thing fixed. So that's going to be 68. Let's see here. 66. All right. Let's do that. Okay. All right. So that's where we get the two different things. I just used on this one, I just used 70 because again, it's like I said, they're not overweight, and that's why I didn't use the ideal body weight in this calculation. Okay.
And I would have done it exactly the same way. I would have
could've
just
done it.
70 kilos.
Yeah, you could put the 66 in here and multiply it by 10. You're still going to come out with the same answer.
You're still in the same range, right?
Right. Still same range, and basically you'll come up with the same answer.
Stephanie,
so-
did that answer your question?
And Stephanie, if
Stephanie
you're
says
if you wanna
yes.
put your mic up, that's fine too. So either way you want
No,
to do
she
that.
typed in an answer and she said, that's it. That's
All
correct.
right, perfect. Okay, thank you so much.
Okay, now, do you want me to unmute them all?
I think I did.
Well, I'm going to do it. There we go.
So
Now, they
anybody
still
that
have
wants
to unmute their
themselves
microphones, I think.
and ask a question, feel free to do so. All right, you guys, now's the time. And all this time I was going to pick on you tomorrow about leaving out and making Kim take over for you, Tom, because you went out to hit the golf course and everything.
Yeah, I wish that's where I was. I mean, I should. It's 78 degrees and sunny, so that's where I should be.
It's nice up here too. It's not 78, but it's about 74 or 3. So,
Okay.
all right.
Ricardo?
Anybody
No.
got anything else?
Looks like Courtney's unmuted. Courtney? No, now she's gone.
All right. Well, how we doing on the chat side? Anything?
No, I don't have any questions.
Nothing popping up there,
Clear as mud.
huh? That's what somebody said.
No, that's what I said.
Oh, okay.
But it covered the ground.
Oh. Yeah. All right.
Okay,
Well, we
I don't
still
see
got a
any.
few people. All right, you guys, this is the last call. Tom and I are going to go ahead and take the rest of the afternoon off if you guys don't have any questions. I don't see my phone burning up yet either, so it looks like no one's.
All right.
So, okay, well, we'll go ahead and sign off. And again, we'll start promptly at our same time, 11 a.m. Eastern Daylight Savings Time in the morning. And we've got a good head start on mechanical ventilation. We will go back over and review some things before we start tomorrow to make sure everybody's on the same sheet and kind of get the cobwebs shook out a little bit. And thank you again, Tom and Kim, for both of you for your help today. I really appreciate it.
Happy to help out. We'll see you tomorrow.
All right, sounds good. Bye.